Hello there, and welcome to Science for Sleep, where curiosity gets cozy and the universe slows down just enough for us to wander through it together. Tonight's journey takes us far beyond the familiar planets of our own solar system to a place that sounds less like a real world and more like something dreamed up by a particularly dramatic weather forecaster after too much coffee. Imagine standing beneath a blue sky while the wind screams faster than the speed of sound. Imagine clouds made not of water vapour, but of silicate particles. Imagine rain, not soft and cold against your skin, but sharp enough to slice through metal. Because somewhere out there in the dark, roughly 64 light-years away from Earth, there truly is a planet where it rains molten glass sideways through the atmosphere. And strangely enough, despite how violent and hostile that world is, it also happens to be one of the most beautiful planets astronomers have ever discovered. Its name is HD 189733b, which admittedly sounds less like a planet and more like a password you would immediately forget after resetting your email account. Astronomers are not always known for poetic naming conventions. Occasionally they discover worlds with oceans of lava, collapsing atmospheres, or storms larger than Earth itself, and then label them something that sounds like a barcode on office equipment. Still, behind the awkward name lies a place so bizarre that even scientists sometimes struggle to describe it without sounding like science fiction writers. Before we drift deeper into this alien storm, though, I'd love to ask you something. Where in the world are you listening from tonight? Is it late evening where you are? Maybe the house has finally gone quiet. Perhaps rain is tapping softly against your own windows right now, thankfully made of ordinary water and not microscopic shards of flying glass moving at several thousand miles per hour. Maybe you're lying in bed after a long day, watching the ceiling slowly blur as sleep creeps closer. Or maybe it's early morning somewhere on the other side of the world, and this little voyage through space is beginning your day instead of ending it. And what time is it for you right now? Funny, isn't it? At this exact moment, people all across Earth are winding down beneath one calm shared sky, while, far away in another solar system, an entire planet is being battered by winds so extreme they would make even the fiercest hurricane on Earth seem almost polite. If you find these quiet explorations soothing, interesting, or simply a pleasant way to slow your thoughts for a while, I'd be ever so grateful if you liked the video and maybe subscribed as well. It helps this sleepy little corner of science continue drifting through the cosmos, one strange world at a time. Now then, get comfortable, settle into your blankets, relax your shoulders, let your breathing slow a little. Tonight we are leaving Earth behind, not with roaring rockets or dramatic countdowns, but gently, quietly, the way all good bedtime journeys should begin. Because somewhere beyond our solar system, orbiting a distant orange star in the constellation Vulpecula, there is a planet where the weather forecast would be difficult to explain without sounding slightly unwell. Winds above 5,000 miles per hour, temperatures climbing beyond 1,000 degrees Celsius, atmospheric pressure fluctuations powerful enough to crush ordinary expectations of weather entirely, and rain made of glass, not metaphorical glass, not frozen crystals that merely resemble it, actual silicate particles heated, melted, lifted into the atmosphere and hurled sideways across the planet by supersonic winds. If Earth's weather can occasionally feel inconvenient, perhaps when your umbrella flips inside out during a storm or your carefully planned picnic dissolves into disappointment beneath dark clouds, HD 189733b takes the concept of bad weather and launches it directly into cosmic absurdity. But to really understand why this planet exists at all, we need to step back for a moment and think about how strange the universe truly is. For most of human history, we only knew of the planets in our own solar system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Familiar names circling our star in neat, predictable paths. Ancient skywatchers observed them wandering across the heavens long before telescopes existed. To many civilizations, they were gods, omens, wandering lights with mysterious personalities. And for a very long time, humans quietly assumed that other stars probably had planets too. It seemed reasonable. After all, if our sun could form worlds, why not the countless other stars scattered across the night sky? But until recently, nobody actually knew. In fact, the first confirmed discovery of a planet orbiting a normal sun-like star did not happen until 1995. That is astonishingly recent when you think about it. Humanity built pyramids, crossed oceans, invented symphonies, argued endlessly on the internet, and landed on the moon before finally proving that planets around other stars were real. Since then, astronomers have discovered thousands of exoplanets, and the moment they began finding them, the universe immediately became much stranger than anyone expected. Some planets orbit 2 stars at once, like the fictional world of Tatooine from Star Wars. Some are so dense they may be composed largely of diamond. Others wander alone through space without any star at all, drifting through the darkness like cosmic orphans. There are worlds where lava oceans glow beneath black skies. Worlds where iron may condense into droplets and fall as metallic rain. Planets larger than Jupiter orbiting absurdly close to their stars, completing an entire year in just a few Earth days. And among these bizarre discoveries sits HD 189733b, one of the most studied exoplanets in human history, partly because it is terrifying, partly because it is scientifically valuable, and partly because, against all logic, it is beautiful. You see, most exoplanets are not photographed directly. They're too distant and too dim compared to their stars. Trying to photograph one directly is a bit like attempting to spot a single grain of dust beside a lighthouse from thousands of kilometers away. Instead, astronomers usually detect planets indirectly. Sometimes they observe a star wobbling very slightly as a planet's gravity tugs on it. Other times they watch for tiny dips in brightness when a planet passes in front of its star. That method, called the transit method, has become one of the most successful techniques in modern astronomy, and HD 189733b turned out to be particularly cooperative. Every couple of days the planet passes directly between its star and Earth, blocking a tiny portion of the starlight, small enough that you would never notice it with your eyes, of course, but large enough for sensitive instruments to detect. That tiny dimming of light revealed the planet's existence. But it also revealed something even more interesting: its atmosphere. When starlight passes through a planet's atmosphere, different gases absorb different wavelengths of light. By carefully studying those changes, astronomers can begin figuring out what an alien atmosphere is made of. It is one of the closest things humanity has to reading the weather report of another world. And what they found surrounding HD 189733b was astonishing. Hydrogen, helium, traces of silicate particles, scorching heat, extreme weather systems, and a deep rich blue colour unlike any exoplanet previously observed. At first glance, the planet almost looks inviting. Photographs released by astronomers show a dark, sapphire-coloured world floating peacefully in space. If you knew nothing about it, you might mistake it for some giant ocean planet. Calm, beautiful, perhaps even habitable. But that blue colour is deeply misleading. On Earth, our sky appears blue because molecules in the atmosphere scatter shorter blue wavelengths of sunlight more effectively than red wavelengths. It is called Rayleigh scattering, and it gives our world its familiar soft blue skies. HD 189733b may share a similar scattering effect, but the atmosphere responsible for it is nothing like Earth's. Instead of calm air and water vapour, its atmosphere is filled with silicate particles and raging storms moving at unbelievable speeds. In other words, the planet is beautiful for roughly the same reason a blowtorch flame can sometimes look beautiful. Distance softens danger. The closer you examine it, the worse things become, and things become worse very quickly. HD 189733b belongs to a category astronomers call hot Jupiters. These are enormous gas giant planets, roughly comparable in size to Jupiter, except they orbit astonishingly close to their parent stars. Our own Jupiter takes nearly 12 Earth years to orbit the Sun. HD 189733b completes an orbit in just over 2 days. 2 days. Imagine if Earth orbited the Sun every 48 hours. The year would barely last long enough to finish your laundry before beginning again. Because the planet sits so close to its star, temperatures rise to extraordinary levels. The atmosphere is heated constantly by intense stellar radiation. One side of the planet permanently faces the star, baking beneath eternal daylight, while the opposite side remains locked in endless night. This is called tidal locking. The same process causes our moon to always show the same face toward Earth. Over time, gravity synchronizes rotation and orbit until one hemisphere permanently faces the object it circles. So on HD 189733b, there is no sunrise or sunset in the way we experience them. One side always burns beneath the star, the other never sees daylight at all, and between those two extremes, unimaginable winds roar continuously across the planet as heat tries desperately to redistribute itself. Here on Earth, hurricanes can reach wind speeds of around 150 miles per hour, strong enough to flatten buildings, uproot trees, and send garden furniture on unexpected adventures through the neighbourhood. On Neptune, the fastest winds in our solar system can exceed 1,200 miles per hour. Impressive. HD 189733b casually exceeds both. Its atmospheric winds may surpass 5,000 miles per hour. That is faster than the speed of sound. The atmosphere itself essentially becomes a planet-wide shockwave, and inside those violent winds travel tiny molten silicate particles, glass, blasted sideways through the atmosphere like microscopic bullets. It is difficult to overstate how hostile this environment truly is because our brains instinctively compare it to Earth weather. Rain, wind, clouds, storms, familiar concepts. But alien planets often take familiar ideas and push them beyond anything evolution prepared us to visualize. Rain on Earth falls downward because gravity pulls water droplets through relatively calm air. On HD 189733b, the winds are so violent that the glass rain likely falls sideways instead. Imagine standing in a sandblaster during a hurricane while inside an industrial oven travelling faster than a fighter jet. Now make it hotter and louder and endless. That is closer to the reality of this world. Not exactly ideal beach holiday conditions. Though somewhere, one overly optimistic travel agency would probably still advertise it as an unforgettable experience. What makes all of this especially fascinating is that HD 189733b is not unique in being strange. In fact, one of the biggest lessons modern astronomy keeps teaching us is that the universe seems remarkably comfortable producing worlds far more extreme than anything we once imagined possible. For generations, science fiction writers invented bizarre alien planets because it made stories more exciting. Then astronomers began discovering actual planets, and the universe calmly responded, "Oh, you thought that was imaginative? Watch this." And perhaps that is one of the most comforting things about space. No matter how much we discover, reality continues to remain stranger than fiction. Somewhere right now, while Earth rotates quietly beneath your room tonight, this distant planet is enduring a storm unlike anything human beings have ever experienced. A storm powered by gravity, radiation, chemistry and motion. A storm raging endlessly beneath a blue alien sky. And the remarkable thing is that we know about it at all. Tiny primates on a small rocky planet somehow learned enough physics, mathematics and engineering to study the atmosphere of a world 64 light-years away. That alone feels slightly miraculous, especially when you remember that humans still occasionally forget why they walked into a room. Yet despite our confusion, our mistakes, our endless tendency to lose passwords and overcook pasta, we built instruments capable of examining the weather on a planet orbiting another star. And that weather turned out to involve sideways glass rain. The universe really does reward curiosity with the most unexpected answers. Still, the deeper astronomers looked into HD 189733b, the stranger the planet became. Because beneath that famous blue colour and those violent storms lies a story about how scientists learn to study worlds they cannot directly touch, visit, or even properly photograph. Long before anyone knew that HD 189733b contained storms of flying glass and winds faster than sound, it was simply another ordinary-looking star sitting quietly in the constellation Vulpecula. Nothing about it would immediately capture your attention if you saw it in the night sky. No dazzling brightness, no dramatic colour, no visible planets circling around it like tiny ornaments. Just another distant point of light among countless others. And yet, hidden around that modest little star was one of the strangest planets humanity would ever discover. The fascinating thing about exoplanets is that, for most of human history, they existed only as suspicion. People imagined them, hoped for them, argued about them philosophically, but nobody could prove they were there. Even as late as the 1980s, the idea of planets orbiting other stars still felt uncertain enough that many astronomers approached the subject cautiously. Today, of course, exoplanets are almost routine discoveries. Thousands have been catalogued. Some are rocky, some are enormous gas giants. Some may even have conditions suitable for liquid water. But finding them is astonishingly difficult because stars are overwhelmingly bright compared to the worlds orbiting them. Imagine trying to spot a tiny dust particle floating beside a stadium floodlight from hundreds of kilometers away. That is roughly the challenge astronomers face. Stars dominate everything around them. Their light floods telescopes, overwhelms detectors, and hides nearby planets almost completely. Even giant planets, many times larger than Earth, become practically invisible next to the stars they orbit. So astronomers had to become clever, very clever. Instead of looking directly for planets, they began searching for the effects planets have on their stars. Because even though stars are enormous, planets still tug on them gravitationally. A star does not simply sit motionless while planets orbit around it. Technically, both star and planet orbit a shared centre of mass. The star moves only slightly, of course, but with sensitive enough instruments that tiny motion can be detected. This became one of the earliest successful methods for discovering exoplanets. Astronomers would examine starlight carefully, searching for subtle shifts caused by the star wobbling toward and away from Earth. As the star moved closer, its light shifted slightly toward blue wavelengths. As it moved away, the light shifted toward red. This technique is called the radial velocity method, though admittedly that sounds less like astronomy and more like something your doctor warns you about after age 40. Still, it worked beautifully. And in the early 2000s, astronomers using this method began identifying more and more planets orbiting distant stars. Many of those early discoveries were surprising. Scientists had expected solar system resembling our own, with smaller rocky planets near stars and massive gas giants orbiting farther away. After all, that was the only example humanity had. Instead, the universe immediately started breaking expectations. Huge planets were discovered orbiting absurdly close to their stars. Worlds larger than Jupiter whipped around their suns in mere days. Astronomers called them hot Jupiters, and at first they seemed almost ridiculous. Gas giants are supposed to form far from stars where temperatures are low enough for icy material to accumulate. Jupiter itself formed far out in the colder regions of our solar system. So why were these giant planets practically hugging their stars? Nobody fully understood yet. The universe, as usual, was under no obligation to match human assumptions. Then, in 2005, astronomers studying a star known as HD 189733 noticed something interesting. The star itself sits about 64 light-years from Earth. In cosmic terms, that is actually fairly close. The Milky Way galaxy stretches roughly 100,000 light-years across, so HD 189733 is practically in our galactic neighbourhood. If the galaxy were the size of Earth, this star system would still be closer than your nearest grocery store. Of course, close in space remains hilariously impractical by normal human standards. Light, travelling at roughly 300,000 kilometers per second, still takes 64 years to get there. If you somehow boarded a modern spacecraft and attempted the journey using current technology, you would arrive sometime after several future civilizations had probably argued online about entirely different problems. Space has a very rude habit of making even nearby destinations feel impossible. But astronomically speaking, HD 189733 was close enough for scientists to study carefully, and that mattered enormously. The star itself is slightly smaller and cooler than our Sun. It belongs to a category called orange dwarfs, or K-type stars. These stars are quite common throughout the galaxy, and often live longer than larger stars like our Sun because they burn their fuel more slowly. If stars were candles, giant blue stars would be enormous fireworks burning brightly and dying quickly, while orange dwarfs would be steady lanterns patiently glowing for billions upon billions of years. HD 189733 itself is somewhat active and energetic. Its surface occasionally erupts with stellar flares and magnetic disturbances. Not exactly ideal for peaceful planetary weather. But astronomers were not initially focused on the star. Their attention shifted because they noticed tiny periodic changes in its motion. Something massive appeared to be orbiting it. And then came the truly important observation. The planet passed directly in front of the star from Earth's perspective. This was extraordinarily lucky. Most planetary systems are tilted at angles where planets never cross between their stars and Earth. But HD 189733b happened to orbit in just the right alignment for astronomers to witness transits regularly. Every time the planet crossed the star's brightness dipped ever so slightly. Not much, just a tiny decrease, but enough. That tiny flicker of dimming light changed everything because transiting planets allow astronomers to learn far more than wobbling stars alone ever could. Once scientists can measure how much starlight a planet blocks, they can estimate the planet's size. Combine that with measurements of the star's wobble, and they can calculate the planet's mass. From there, they can estimate density, and suddenly, a distant invisible object starts becoming a real physical world, a place. Not merely a mathematical signal buried inside telescope data. HD 189733b turned out to be enormous, roughly the size of Jupiter, though somewhat more massive, and alarmingly close to its star. The planet orbits at a distance of only about 4.7 million kilometers. Now that may still sound enormous because human brains are not especially good with astronomical distances, but consider this. Mercury, the closest planet to our Sun, stays roughly 58 million kilometers away. HD 189733b sits more than 10 times closer to its star than Mercury does to ours. It is unbelievably close. If this planet existed in our solar system, it would not merely orbit inside Mercury's path, it would practically skim the Sun's atmosphere. And because of that proximity, the planet completes an orbit incredibly quickly. A single year on HD 189733b lasts just over 2 Earth days. Imagine celebrating birthdays every weekend. Though admittedly on this particular planet, survival long enough to enjoy cake might prove challenging. As astronomers continued observing the world, they began realizing just how valuable it was scientifically. Because the planet transits so frequently and because the system lies relatively close to Earth, HD 189733b became one of the best candidates for atmospheric studies. This is where things started becoming truly extraordinary. You see, when a planet passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere before reaching Earth. Different chemicals absorb different wavelengths of light. Hydrogen absorbs certain wavelengths, Sodium absorbs others. Water vapor leaves its own fingerprints. By analysing these patterns carefully, astronomers can identify the atmospheric composition of worlds they cannot directly see, which is honestly one of the most impressive things humans have ever figured out. Think about it for a moment. Our species evolved on a small rocky world where early humans worried mainly about predators, weather, and whether berries were poisonous. Then, after enough generations, we somehow invented spectroscopy and started analysing alien atmospheres across interstellar distances. Human intelligence really took a dramatic turn somewhere along the line. Using instruments like the Hubble Space Telescope and later other observatories, scientists studied HD 189733b intensely. And almost immediately the planet began revealing bizarre secrets. First came the temperatures, extremely high. The atmosphere was scorching, reaching temperatures above 1000 degrees Celsius in many regions. Then came evidence of water vapor. Now whenever people hear water, excitement tends to follow because water on Earth is associated with life. Oceans, rain, rivers, clouds, comfortable things. But on HD 189733b, water vapor does not suggest tropical beaches and peaceful coastlines. At those temperatures, water exists as superheated vapor inside a raging inferno atmosphere. Context matters enormously in astronomy. Oxygen, water, carbon. Familiar ingredients can produce wildly unfamiliar worlds. Then scientists noticed something else. The planet appeared blue. This was astonishing because most exoplanets do not reveal visible colour information clearly enough for us to describe them aesthetically. Yet HD 189733b displayed a rich cobalt blue appearance unlike anything previously observed on another world. For a brief moment, the planet almost sounded inviting. Blue worlds trigger something emotional in human beings because Earth itself is blue. We associate blue planets with oceans, calm skies, and life. But the resemblance turned out to be deeply deceptive. The blue coloration likely comes from silicate particles scattering blue light in the atmosphere. Not peaceful oceans, not clear skies. Tiny particles of glass suspended in supersonic winds. Which somehow makes the planet both more horrifying and more fascinating simultaneously. As telescopes improved, scientists began constructing temperature maps of the planet's atmosphere. That sentence alone would sound impossible to someone living a century ago. Temperature maps of a planet orbiting another star. Yet astronomers managed it. By observing infrared emissions from different parts of the planet during orbit, researchers could estimate temperature variations across the atmosphere. What they discovered was violent heat redistribution. The side permanently facing the star absorbed enormous energy continuously. But instead of heat remaining fixed there, powerful winds transported it across the planet. Those winds became some of the fastest ever measured anywhere, several thousand miles per hour, faster than sound itself. On Earth, weather systems are shaped by sunlight, rotation, oceans, mountains, and atmospheric pressure differences. Hurricanes and jet streams emerge from complicated interactions between heat and motion. Now imagine removing continents entirely, remove oceans, increase temperatures enormously, place the planet incredibly close to a star, lock one side permanently toward daylight, then superheat the atmosphere until global winds become planet-wide shockwaves. That is the environment astronomers were uncovering. And yet the deeper scientists studied HD 189733b, the more valuable the planet became. Because strange worlds are often scientifically useful worlds, extreme environments test our understanding of physics and atmospheric chemistry. They force scientists to refine models, improve theories, and rethink planetary formation itself. Hot Jupiters in particular completely changed ideas about how solar systems evolve. Originally, astronomers believed giant planets formed far from stars and stayed there permanently, but hot Jupiters proved otherwise. The These worlds likely formed farther out before migrating inward over time through gravitational interactions with disks of gas or neighbouring planets. Planetary systems, it turns out, are not static, peaceful arrangements. They are dynamic, chaotic, restless. Worlds move, orbits shift, entire planets can migrate inward toward destruction. Our own solar system now appears somewhat unusually stable compared to many others, which is mildly comforting, though space has a habit of remaining unpredictable whenever humans become too comfortable. As years passed, HD 189733b became one of the most frequently studied exoplanets ever discovered. Hubble observed it, Spitzer observed it, ground-based telescopes tracked it endlessly. Scientists monitored atmospheric escape, stellar activity, thermal redistribution, and chemical composition. At one point, astronomers even detected evidence that the planet's atmosphere was being stripped away by radiation from its star. The star itself appeared to be actively eroding the planet. Imagine weather so severe that your atmosphere is literally leaking into space. Again, not ideal vacation conditions. And yet, for all its violence, HD 189733b also represented something hopeful. Because every improvement in exoplanet science brings humanity closer to understanding not just extreme alien worlds, but potentially habitable ones too. The same techniques used to analyse this hellish gas giant may eventually detect biosignatures on smaller Earth-like planets. Oxygen, methane, perhaps even evidence of life itself. That possibility hangs quietly behind every exoplanet discovery, even when the planet itself is essentially a cosmic nightmare. In a strange way, worlds like HD 189733b serve as stepping stones. We learn by studying extremes first. The easiest planets to detect are often the largest and hottest because they produce stronger signals. Giant close-orbiting planets tug harder on stars and block more light during transits. So humanity's first glimpse into alien solar systems revealed the loudest, most dramatic worlds first. The cosmic equivalent of walking into a room and immediately noticing the person screaming. Only later do subtler worlds begin emerging from the data. Small rocky planets, potentially temperate planets, quiet planets. But before we reach those calmer discoveries, astronomy still has much to learn from violent places like HD 189733b. Because this planet does not merely challenge our understanding of weather or atmospheres, it challenges our instincts about what planets are supposed to look like altogether. After all, despite everything scientists learned about its terrifying conditions, despite the crushing heat and supersonic storms and sideways glass rain, one detail continued capturing public imagination more than anything else. The planet was blue, beautifully blue. There is something about the colour blue that immediately softens the human mind. Blue feels calm, safe, familiar. We paint bedrooms blue to make them relaxing. Airlines use blue logos because it feels trustworthy. Oceans, lakes, clear summer skies, distant mountains fading into soft blue haze, all of it quietly teaches the brain the same lesson over and over again. Blue usually means peace, which is precisely why HD 189733b is so unsettling. Because at first glance it does not look like a hell planet at all. It looks beautiful. Not merely interesting in a scientific sense, but genuinely beautiful in the way Earth is beautiful from space. Rich cobalt tones swirl across the planet's atmosphere. Against the darkness of space, the world glows with a deep sapphire colour that almost resembles a tropical ocean seen from orbit. If you showed the image to someone unfamiliar with astronomy, they might guess it was an artistic rendering of some distant paradise world. A place with warm seas and gentle skies, perhaps islands hidden beneath clouds, maybe strange alien birds soaring over endless blue water. The reality, unfortunately, is closer to being trapped inside a giant industrial sandblaster while standing next to a jet engine inside a furnace. Space has a remarkable sense of irony sometimes. The famous blue colour of HD 189733b became one of the most talked about aspects of the planet, after astronomers working with the Hubble Space Telescope released observations suggesting the world truly appeared deep blue in visible light. This was an important moment because exoplanets are extraordinarily difficult to study visually. Most are too distant and too overwhelmed by the brightness of their stars for us to resolve clear images. In fact, many of the pictures people see of exoplanets are actually artistic interpretations based on scientific data rather than direct photographs. That is not deception, by the way. It is simply practicality. Telescopes often collect information about temperature, composition, brightness, and spectral characteristics rather than detailed camera-style images. Imagine hearing footsteps in another room and reconstructing the person from sound alone. Astronomy frequently works like that. Scientists gather clues and carefully piece worlds together, but HD 189733b stood out, because astronomers were able to analyse changes in light during the planet's orbit carefully enough to estimate its visible colour, and the answer was startling. Blue. Very blue. Deeper and richer than Earth in some ways, almost jewel-like. Naturally, this immediately triggered comparisons to our own planet. Earth is often called the blue planet because oceans cover most of its surface. Seen from space, sunlight reflects off vast bodies of water, while the atmosphere scatters blue wavelengths of light across the sky. Blue, for us, means life. So the discovery of another blue world carried emotional weight even before people understood the actual conditions there. Humans are extremely good at projecting familiarity onto unfamiliar things. We see faces in clouds, personalities in pets, intentions in malfunctioning printers, and when we see a blue planet, part of the brain instinctively whispers, maybe it's a little like home. HD 189733b is not like home, not even remotely. The blue appearance comes from something far more hostile. Tiny silicate particles suspended high in the atmosphere scatter blue wavelengths of light, while absorbing redder wavelengths. In principle, this is somewhat similar to how Earth's atmosphere scatters sunlight. But the material involved is completely different. On Earth, atmospheric scattering happens in relatively gentle conditions involving nitrogen, oxygen, and microscopic molecules drifting peacefully through air. On HD 189733b, the atmosphere contains particles associated with molten glass, and those particles exist inside a raging storm system, unlike anything in our solar system. The universe, apparently, enjoys taking comforting visual cues and attaching them to terrifying realities. Still, the beauty of the planet is real, and perhaps that says something interesting about beauty itself. After all, many dangerous things are beautiful from a distance. Volcanoes glowing beneath the night sky, lightning storms rolling across open plains, hurricanes seen from orbit. Even on Earth, nature often combines elegance and violence in deeply unsettling ways. HD 189733b simply takes that contrast and amplifies it to cosmic extremes. One reason the planet fascinates scientists so much is because it challenges our expectations about what weather and atmospheres can actually look like. For most of human history, weather meant Earth weather: rain, snow, clouds, wind. Perhaps if you lived somewhere particularly dramatic, maybe hailstorms large enough to threaten your car insurance premiums. But once astronomers began studying exoplanets seriously, weather itself suddenly expanded into something much stranger. There are worlds where temperatures become high enough to vaporize rock, worlds where clouds may contain iron droplets, planets with methane rain, atmospheres made largely of hydrogen and helium, storms larger than entire planets. HD 189733b belongs firmly within this category of alien meteorological absurdity. And yet, because it is blue, people remember it emotionally in a way many exoplanets never achieve. Colour matters deeply to human perception. Mars is red, Neptune is blue, Saturn is golden. Those colours become identities. A planet's colour shapes how we imagine it long before we understand its physics. In the case of HD 189733b, the colour creates an almost uncomfortable contradiction between appearance and reality. If you could somehow float safely above the atmosphere without immediately being vaporised, the view might actually look magnificent. The star nearby would burn with orange light. The planet's atmosphere would shimmer deep blue beneath violent cloud systems. The surrounding darkness of space would make the colours appear even more vivid. And beneath all that beauty, the atmosphere itself would be trying enthusiastically to destroy absolutely everything. It is difficult to picture because human brains naturally associate visual beauty with safety. Evolution encouraged that tendency. Clear water looks inviting because clean water helped survival. Healthy skies meant stable weather. Warm colours in fruit suggested ripeness. But the universe beyond Earth does not necessarily follow Earth's rules. An alien planet can look serene while hiding conditions beyond anything human biology could endure. An HD 189733b is not merely hot, it is catastrophically hot. Temperatures on the day side may exceed 1000 degrees Celsius, hot enough to melt many metals. The atmosphere itself becomes a chemically violent environment where molecules behave differently than they would under Earth conditions. Silicates can vaporize, cloud chemistry becomes exotic, atmospheric circulation turns extreme. This is not weather in the familiar sense anymore. It is planetary physics pushed toward absurd limits. The blue colour also highlights something fascinating about exoplanet science itself. Astronomers are not simply cataloguing distant objects anymore. They are beginning to study actual atmospheric dynamics on worlds orbiting other stars. That sentence would have sounded almost magical only a few generations ago. Think about the level of knowledge involved. Humans learned that stars are suns, then learned that planets orbit other suns, then learned how to detect those planets, then learned how to estimate atmospheric composition, then learned how to analyse weather systems, and eventually discovered a blue planet where it rains glass sideways. Science progresses in wonderfully strange directions sometimes. What makes HD 189733b particularly useful is its size and orbit. Because the planet is large and transits frequently, astronomers can gather repeated observations relatively easily compared to smaller exoplanets. Repeated observations are extremely valuable because atmospheres are complicated. Light passing through atmospheric layers contains enormous amounts of information, but also enormous amounts of noise and uncertainty. Stars themselves fluctuate. Instruments contain limitations. Signals become distorted. Researchers must carefully separate planetary data from everything else happening around it. Astronomy often resembles trying to reconstruct an orchestra performance while listening through several walls during a thunderstorm, and yet scientists keep succeeding. As telescope technology improved, researchers began measuring not just colour but thermal emissions, atmospheric escape, and wind distribution across HD 189733b. The planet essentially became a laboratory for understanding extreme atmospheres. One particularly astonishing discovery involved the difference between the planet's hottest region and the location directly facing the star. Intuitively, you might expect the point receiving maximum starlight to be hottest, but observations suggested the hottest region was shifted eastward. Why? Because the winds were so powerful that they physically transported heat across the atmosphere faster than the planet could radiate it away. Imagine weather systems so violent that the entire thermal structure of the atmosphere gets dragged sideways. Earth's jet streams influence weather dramatically, of course. They steer storms, affect temperatures, and shape seasonal patterns. But HD 189733b operates on another level entirely. Its atmosphere behaves less like normal weather and more like a planetary engine running at impossible speeds. And all of this hides beneath that deceptively calm blue appearance. There is something almost philosophical about that contrast. Humans spend much of life interpreting surfaces, faces, colours, expressions, Appearances. We instinctively trust visual impressions because vision became our primary survival tool. But the universe repeatedly reminds us that appearances can be wildly misleading. Venus shines beautifully in Earth's skies, bright enough to cast shadows at times. Ancient cultures associated it with love and beauty. In reality, Venus is a crushing greenhouse inferno hot enough to melt lead. Neptune appears cool and tranquil from a distance, yet contains some of the fastest winds in the solar system. Even Earth itself can appear peaceful from orbit, while hurricanes, earthquakes, wars and storms unfold below. HD 189733b simply exaggerates that lesson dramatically. Beautiful things are not always gentle, and dangerous things are not always ugly. Scientists also became interested in whether the blue colour might vary over time depending on atmospheric conditions. Weather patterns on hot Jupiters remain an active field of study because these worlds are dynamic rather than static. Cloud layers may shift, temperatures fluctuate, stellar activity changes atmospheric chemistry. Entire circulation systems evolve over time. Earth's weather changes constantly because atmospheres are inherently chaotic systems. Small disturbances can produce large consequences. Tiny pressure variations eventually become storms. Now imagine chaos inside a superheated gas giant orbiting dangerously close to an active star. Predicting such atmospheres becomes extraordinarily difficult, and this is part of why exoplanet science has become so exciting in recent decades. Astronomers are no longer merely discovering planets, they are beginning to study climates, meteorology, seasonal patterns, cloud chemistry. The field is evolving from planetary detection into planetary understanding. Of course, HD 189733b itself remains completely uninhabitable by any Earth standard. That point cannot really be overstated. Sometimes media headlines about exoplanets accidentally create confusion by emphasizing dramatic details while downplaying basic survivability. People hear water vapor and imagine oceans. They hear clouds and picture skies. But conditions matter enormously. A cloud on Earth and a cloud on HD 189733b may share a name while existing in utterly different realities. Language itself struggles with alien worlds because our vocabulary evolved for Earth environments. Even words like rain become slightly misleading. Rain on Earth suggests cool droplets falling peacefully through air. Rain on HD 189733b means molten silicate particles blasted sideways at thousands of miles per hour. Technically similar, emotionally very different. Still, despite all its violence, HD 189733b captured public imagination precisely because it feels vivid. Many exoplanets remain abstract numbers to non-scientists. Mass, orbit, temperature. Interesting perhaps, but emotionally distant. This planet feels tangible. You can picture it. The blue glow, the roaring winds, the sideways storms. The contrast between appearance and reality gives the world personality in a strange way. Not a friendly personality, admittedly. More the sort of personality that would probably destroy your spacecraft before you finish parking. But memorable nonetheless. And there is another reason this planet matters. By learning how atmospheres behave under extreme conditions, astronomers improve the tools needed to study smaller and potentially habitable worlds later. Every atmospheric model refined using hot Jupiters helps future observations of Earth-like planets become more accurate. In science, even hostile worlds can become stepping stones toward extraordinary discoveries. One day, perhaps, telescopes will identify unmistakable signs of life on a distant planet. Not merely atmospheric chemistry, but genuine biosignatures. And when that happens, part of the scientific foundation will trace back through years of studying bizarre places like HD 189733b. A giant blue nightmare world quietly helping humanity learn how to read alien skies. If you step outside on a clear afternoon here on Earth and look upward, the sky appears so naturally blue that most of us rarely stop to think about how strange that really is. After all, space itself is black. Sunlight, meanwhile, is white, containing all visible colours mixed together. So why should the atmosphere above us turn blue specifically? It is one of those everyday phenomena that becomes more fascinating the longer you think about it. The universe takes invisible physics, performs it continuously above our heads, and somehow transforms it into something so familiar that we stop noticing entirely. The same basic question eventually became important on HD 189733b as well. Because once astronomers realised the planet appeared deep blue, they immediately wanted to understand why, and the answer revealed just how alien the atmosphere truly is. To understand the blue skies of another world, though, we should probably begin with our own, because Earth's atmosphere turns out to be an excellent introduction to how light behaves when it encounters gases and tiny particles. Sunlight may look white to our eyes, but it actually contains many different wavelengths of light. Red light has longer wavelengths. Blue and violet light have shorter wavelengths. When sunlight enters Earth's atmosphere, those wavelengths interact with molecules in the air. Shorter wavelengths scatter more easily than longer ones. This process is called Rayleigh scattering, named after the British physicist Lord Rayleigh, who studied the phenomenon in the 19th century. Admittedly, Rayleigh scattering sounds less like atmospheric physics and more like a law firm specialising in unfortunate telescope accidents, but the science itself is elegant. Blue light scatters strongly in all directions as sunlight passes through Earth's atmosphere. So when you look up at the sky, you're seeing scattered blue light reaching your eyes from every part of the atmosphere. That is why the daytime sky appears blue. Sunsets, meanwhile, become red and orange because sunlight travels through much more atmosphere near the horizon. The shorter blue wavelengths scatter away before reaching you, leaving longer red wavelengths behind. Simple, beautiful, quietly extraordinary. And on HD 189733b, scientists suspected something similar might be happening, but only partially similar. Because while Earth's atmosphere consists mostly of nitrogen and oxygen under relatively mild temperatures, HD 189733b exists inside conditions so violent that even familiar physics starts behaving in unfamiliar ways. The planet's atmosphere is dominated largely by hydrogen and helium, much like Jupiter. That part is not especially surprising since HD 189733b is a gas giant. But mixed into those gases are particles and chemical compounds exposed to extraordinary heat and pressure. And among those materials are silicates. Now, silicates are incredibly common throughout the universe. Earth itself contains enormous amounts of silicate minerals, sand, rocks, quartz, much of Earth's crust, all rich in silicates. Under normal Earth conditions, silicates remain comfortably solid. You walk across them at beaches, they sit peacefully in mountains. Occasionally they become annoyingly trapped inside your shoes after hiking. But HD 189733b is not operating under normal conditions. Temperatures there become high enough to vaporize certain silicate materials into the atmosphere itself. Imagine heating an entire world until components of rock begin turning into vapor. That is essentially what happens. Once suspended high in the atmosphere, these particles interact with incoming starlight. Shorter blue wavelengths scatter more effectively, creating the planet's striking sapphire appearance, at least from a distance. The closer you examine the atmosphere, the more hostile it becomes. What makes this especially fascinating is that Earth and HD 189733b arrive at visually similar results through wildly different environmental realities. Earth blue skies emerge from calm atmospheric scattering involving breathable air and moderate temperatures. HD 189733b produces blue coloration through superheated silicate particles racing through an inferno atmosphere at supersonic speeds. It is a bit like discovering that two soups contain similar colours, despite one being tomato soup and the other molten lava. Same appearance, very different dining experience. Astronomers became increasingly confident in the blue interpretation after observations using the Hubble Space Telescope measured changes in visible wavelengths during planetary transits. When the planet passed behind its star from Earth's perspective, researchers could isolate subtle differences in the system's brightness. That allowed them to estimate how much blue light the planet reflected, and surprisingly, the planet reflected a substantial amount of blue light while absorbing redder wavelengths more strongly. The data suggested a deep cobalt appearance unlike anything in our solar system, except perhaps Neptune at first glance. But Neptune's blue colour comes largely from methane absorption within a cold outer atmosphere. HD 189733b achieves its colour through heat, silicate haze and atmospheric violence. Again, appearances become deeply misleading. The blue sky of Earth invites life. The blue atmosphere of HD 189733b actively punishes the concept. Still, there is something remarkable about the fact that humans can even determine this information at all. The planet lies 64 light-years away. That means the light astronomers analyse today actually left the planet decades ago. While you're listening to this now, the photons carrying information about HD 189733b began travelling toward Earth long before smartphones existed, long before streaming services, long before much of the modern internet. Those photons crossed trillions upon trillions of kilometres of empty space before finally arriving at telescopes orbiting Earth. And from tiny fluctuations hidden inside that ancient starlight, scientists reconstructed the colour of an alien sky. If that does not qualify as one of humanity's greatest intellectual achievements, it is difficult to know what would. What is particularly interesting is that HD 189733b likely does not possess a sky in the way humans emotionally imagine skies. When people hear the word sky, they picture standing beneath open air looking upward. But gas giants complicate that image because they lack solid surfaces like Earth's. If you somehow descended into HD 189733b, there would not necessarily be a clear boundary where atmosphere ends and ground begins. Instead, pressure and density would gradually increase deeper and deeper until conditions became extreme beyond comprehension. Jupiter works similarly. There is no firm, solid surface where you could comfortably stand holding an umbrella while reconsidering your life choices. Gas giants transition gradually through atmospheric layers into increasingly compressed materials under enormous pressures. HD 189733b likely contains layers of gas compressed into exotic states by gravity and heat. Deeper regions may involve metallic hydrogen and other strange high-pressure physics, and all of that complexity hides beneath the beautiful blue upper atmosphere visible to distant observers. Of course, the colour itself may not appear identical to human eyes if someone could somehow observe the planet directly nearby. Astronomical colour reconstruction involves interpretation based on available wavelengths and instrument sensitivity. Human vision depends heavily on lighting conditions, atmospheric opacity and contrast, so the exact visual experience remains somewhat uncertain. Still, scientists are confident the world genuinely appears blue overall, and that discovery resonated with people emotionally for obvious reasons. Humans have always attached meaning to colours. Red feels warm, green suggests life, black implies emptiness or danger. Blue carries emotional associations with calmness, stability, depth, and familiarity. So when the public learned about a deep blue alien planet, many people instinctively imagined something peaceful before hearing the phrase sideways glass rain. That emotional whiplash probably contributed enormously to the planet's fame. It sounds fictional in exactly the right way. Beautiful, alien, dangerous, understandable enough to picture but strange enough to feel cosmic. And in many ways, HD 189733b became a perfect example of why exoplanet science captures public imagination so strongly. For centuries, planets were mostly nearby objects within our own solar system. We could observe them through telescopes, map their surfaces roughly, and speculate about their conditions. But exoplanets changed everything because suddenly the galaxy filled with entirely new categories of worlds. Not merely more planets, different planets. Worlds operating under physical conditions humanity had never encountered before. And yet, despite all their differences, many still contain strangely familiar features. Clouds, rain, wind, atmospheres, colour. The details become alien, but the broad concepts remain recognisable enough for the imagination to engage. HD 189733b sits perfectly inside that unsettling middle ground between familiar and incomprehensible. You can imagine blue skies, you can imagine storms, you can imagine rain. Then the details begin arriving one by one. The rain is molten glass. The winds exceed the speed of sound. The temperatures melt metal. The atmosphere itself may strip material from the planet into space. And suddenly, the familiar becomes monstrous. The planet's blue appearance also raised interesting questions about atmospheric haze and cloud formation on hot Jupiters generally. Clouds on Earth form when water vapor cools and condenses around microscopic particles. On HD 189733b, however, cloud formation likely involves completely different chemistry. At sufficiently high temperatures, materials normally considered solid can behave more like atmospheric substances. Silicate droplets may condense, exotic mineral clouds may form, iron vapor may exist in certain atmospheric layers on some hot exoplanets. It sounds almost absurd because human experience evolved within a very narrow environmental range. We instinctively think of rock as solid, water as liquid, and weather as water-based because Earth conditioned us that way. But planetary physics across the galaxy does not particularly care about human intuition. Increase temperatures enough and rocks vaporize. Increase pressure enough and gases become metallic. Move close enough to a star and entire atmospheric systems become gigantic thermodynamic engines. Hot Jupiters especially force scientists to rethink atmospheric chemistry under extreme irradiation. These planets absorb enormous stellar energy because of their close orbits. Many are tidally locked, meaning one side permanently faces the star while the opposite side remains dark. This creates staggering temperature differences across the atmosphere. Heat redistribution becomes crucial. Without strong winds, the day side would become vastly hotter, while the night side cooled dramatically. Instead, atmospheric circulation attempts to move energy around the planet continuously, and on HD 189733b, that circulation became violent enough to shape the entire atmospheric structure. The blue haze visible from afar exists inside a storm system, operating on scales difficult for human minds to visualize comfortably. Earth's atmosphere feels large to us because we live inside it. Hurricanes span hundreds of kilometers, jet streams influence continents, thunderstorms tower into the upper atmosphere. Now imagine weather systems encompassing an entire gas giant larger than Jupiter, and then accelerate those systems until the winds themselves become supersonic. The atmosphere of HD 189733b is less like ordinary weather and more like a continuously detonating planetary machine. Yet somehow, from 64 light-years away, all of that violence compresses visually into one beautiful blue dot. There is something strangely humbling about that. Distance softens chaos. Even Earth from orbit appears peaceful despite everything happening below. Wars disappear, traffic disappears, noise disappears. Seen from far enough away, even violent worlds become quiet. Perhaps that is why astronomy often feels emotionally calming despite studying catastrophic things. Supernovas explode, black holes consume matter, stars die, planets endure endless storms of molten glass, and yet the vastness of space wraps everything in silence. HD 189733b may be one of the most hostile worlds humanity has ever studied, but from a telescope's perspective it still glows serenely blue against the darkness. And the deeper scientists investigated that atmosphere, the more astonishing its weather began to appear. When most people think about wind, they picture something relatively manageable. A cool breeze moving through trees, air pushing against your coat on a winter evening, maybe a strong storm bending umbrellas inside out while someone nearby regrets wearing a hat. Even hurricanes, for all their destructive power, still belong to a category of weather the human brain can emotionally process. Terrifying certainly, but familiar terrifying. Earth terrifying. HD 189733b operates in an entirely different category. Its atmosphere does not simply contain strong winds. The atmosphere itself has essentially become a planet-wide engine of violence. And the truly astonishing part is that scientists managed to measure those winds from 64 light-years away. That still sounds faintly impossible when you say it out loud. Human beings measured the speed of alien winds on a world orbiting another star. Civilization really has come a remarkably long way from poking suspicious berries with sticks. The discovery of these extreme winds emerged gradually as astronomers studied the atmosphere more carefully using spectroscopy and infrared observations. Once scientists realized HD 189733b was tidally locked, meaning one side permanently faced its star while the opposite side remained in eternal darkness, they immediately understood that the atmosphere had a serious problem: heat imbalance, an enormous one. The day side of the planet absorbs staggering amounts of stellar radiation continuously. Temperatures there climb above 1000 degrees Celsius. Some estimates place certain atmospheric regions even hotter, depending on altitude and chemical composition. Meanwhile, the night side receives no direct starlight at all. Now, on Earth, temperature differences drive weather constantly. Warm air rises, cold air sinks. Pressure systems form. Winds emerge as the atmosphere attempts to redistribute energy around the planet, but Earth rotates relatively slowly compared to the atmospheric chaos unfolding on HD 189733b. We also possess oceans, continents, polar regions, seasonal cycles, forests, mountains, and countless stabilizing systems interacting together. HD 189733b is a gas giant orbiting dangerously close to its star. Everything becomes amplified. Imagine placing an entire planetary atmosphere beside an enormous cosmic blowtorch and forcing one side to absorb intense heat endlessly without relief. The atmosphere cannot simply sit still under those conditions. Heat must move somehow, and it moves violently. Astronomers first noticed something strange when mapping temperature distributions across the planet. You might logically expect the hottest point to sit directly beneath the star at the exact centre of the dayside hemisphere, but observations showed the hottest region had shifted eastward. That detail was incredibly important. It suggested the atmosphere itself was physically transporting heat across the planet through powerful winds. Not just strong winds, extraordinary winds. Researchers eventually estimated atmospheric speeds reaching roughly 5,000 to 6,000 miles per hour. That is difficult to visualize properly, because human experience contains almost nothing remotely comparable. Commercial airplanes cruise around 550 miles per hour. The speed of sound at Earth sea level is about 767 miles per hour. A rifle bullet may travel around 1,700 miles per hour. The winds on HD 189733b exceed all of those comfortably. The atmosphere itself is moving faster than sound. Imagine standing inside a hurricane where the air is travelling several times faster than a fighter jet. Now heat that hurricane until metals begin melting, then fill it with silicate particles. That is closer to the reality astronomers uncovered. On Earth, supersonic motion is generally associated with specialized machines. Jets produce sonic booms because they move faster than sound waves can propagate through air. Pressure builds into shock waves, but on HD 189733b, the weather itself may generate shock structures across the atmosphere. The entire planet behaves less like a normal weather system and more like a continuously detonating thermodynamic experiment. And remarkably, this violence likely never truly stops. Earth storms form and dissipate. Hurricanes eventually weaken. Tornadoes die out. Even powerful weather systems remain temporary because Earth's climate redistributes energy relatively efficiently over time. But HD 189733b receives relentless stellar radiation every moment of every orbit. There are no calm seasons, no peaceful atmospheric resets. The engine driving those winds remains permanently active. One hemisphere bakes beneath constant daylight, while the other side cools in endless darkness. The atmosphere exists in a state of continuous planetary imbalance, and imbalance creates motion. Scientists believe the heat difference between day and night sides powers gigantic atmospheric circulation patterns wrapping around the entire world. Hot gas expands and rushes toward cooler regions, while cooler material cycles elsewhere through the atmosphere. Because the planet rotates quickly relative to its orbital period, Coriolis forces likely shape those winds into powerful eastward jets. Similar forces operate on Earth, steering hurricanes and shaping jet streams, but again, HD 189733b pushes every familiar concept to absurd extremes. Earth's jet streams move around 100 to 250 miles per hour. Impressive, useful for ruining airplane schedules occasionally, but tiny compared to what happens on hot Jupiters, and HD 189733b may not even represent the absolute upper limit of exoplanet weather. Other hot Jupiters could potentially host similarly violent or even more extreme atmospheric dynamics depending on temperature, composition, and stellar irradiation. The universe appears surprisingly enthusiastic about creating nightmare weather systems. One fascinating aspect of these winds is how they influence atmospheric chemistry itself. On Earth, atmospheric layers remain relatively stable in composition overall. Oxygen stays oxygen. Nitrogen stays nitrogen. Water cycles through evaporation and condensation, but the chemistry remains familiar. On HD 189733b, however, the atmosphere becomes a dynamic chemical battlefield. Temperatures vary enormously between regions. Materials vaporize on the day side. Winds transport compounds rapidly across the globe. Cooling may allow certain materials to condense temporarily before being reheated elsewhere. The entire atmosphere becomes chemically restless. And inside those supersonic winds travel the famous silicate particles responsible for the planet's blue appearance. Which means the weather is not merely fast, it is abrasive, violently abrasive. The phrase glass rain often captures headlines because it sounds dramatic, but the reality is even stranger than most headlines suggest. Scientists believe molten silicate particles may condense into droplets or grains within cooler atmospheric regions. Then the winds seize those particles and hurl them sideways through the atmosphere at extraordinary speeds. On Earth, sandstorms can already become dangerous because tiny particles travelling through strong winds erode surfaces aggressively. Dust storms damage machinery, strip paint, and reduce visibility dramatically. Now replace ordinary dust with hot silicate material accelerated by supersonic planetary winds. The atmosphere itself essentially becomes a giant cutting tool. And because HD 189733b lacks a solid surface in the familiar sense, these storms likely operate through vast atmospheric layers continuously. There is no peaceful ground level where conditions suddenly improve. Deeper atmospheric layers simply become hotter and denser. Interestingly, scientists did not directly see these winds in the way meteorologists observe storms on Earth. Instead, researchers inferred wind speeds through careful analysis of spectral shifts and heat distribution. One major breakthrough came from studying carbon monoxide signatures in the atmosphere. By observing slight Doppler shifts in spectral lines during transits, astronomers could estimate how atmospheric gases moved relative to Earth. The atmosphere itself left fingerprints inside the starlight. and those fingerprints revealed astonishing motion. Again, this level of science borders on magical when viewed from the perspective of everyday life. Someone forgets where they placed their glasses for 20 minutes. Then later, that same species measures atmospheric circulation on a world trillions of kilometers away. Humanity contains strange contrasts. What makes HD 189733b especially compelling scientifically is that its atmosphere allows researchers to test atmospheric circulation models under extreme conditions impossible to reproduce fully on Earth. Planetary atmospheres obey physics universally, but environmental conditions vary wildly. By studying how atmospheres behave elsewhere, scientists refine broader theories about fluid dynamics, heat transport, chemistry, and climate systems generally. Even Earth science benefits indirectly from exoplanet studies. And there is another fascinating layer to all of this. Weather on Earth feels enormous to us because we are tiny creatures living inside it. Thunderstorms appear gigantic from the ground, hurricanes span entire coastlines. The atmosphere dominates daily life so completely that humans built civilizations around predicting it. Farmers depended on rain, sailors depended on wind, entire cultures formed around seasonal patterns, weather shaped history. But HD 189733b reminds us that Earth weather exists within a surprisingly gentle range compared to what the universe allows. Our planet sits in an unusually stable and moderate environment. The atmosphere remains thin enough for comfortable breathing yet thick enough for climate regulation. Temperatures support liquid water. Wind speeds rarely become unsurvivable outside extreme storms. Earth, in many ways, is meteorologically calm. The more astronomers study exoplanets, the more unusual that calmness begins to appear. Some worlds experience tidal heating so intense their surfaces melt. Others orbit red dwarf stars bombarded constantly by stellar flares. Some may possess atmospheres hundreds of times denser than Earth's. And worlds like HD 189733b endure atmospheric violence almost beyond intuition. The planet also demonstrates something important about the relationship between stars and planets. Stars are not passive background objects. They dominate planetary evolution profoundly. Distance from a star influences temperature, atmospheric chemistry, radiation exposure, weather systems, orbital stability, and potentially even whether life can emerge at all. HD 189733b sits so close to its star that the star essentially controls the planet's entire existence. The atmosphere responds continuously to stellar energy input. And because the star itself remains somewhat active magnetically, stellar flares and radiation bursts may further disturb atmospheric conditions periodically. Imagine living beside a furnace that occasionally erupts violently, while your entire world races around it every 2 days. Not exactly relaxing. Of course, no humans will ever stand inside those winds. At least almost certainly not. The temperatures alone would destroy ordinary spacecraft rapidly, and the atmospheric pressures deeper down become increasingly catastrophic. Even robotic exploration would be enormously challenging using anything remotely resembling current technology. So for now, HD 189733b remains something humanity studies from afar, a distant laboratory of atmospheric extremity. And perhaps that distance itself contributes to why astronomy feels comforting despite describing terrifying things. You can safely contemplate impossible storms when separated by 64 light-years. The danger remains intellectual rather than immediate. There is something strangely cozy about that arrangement. The universe performs gigantic, violent experiments endlessly, while we observe quietly from beneath blankets with tea nearby. Rain is usually considered comforting. There is a reason people fall asleep to recordings of it. Soft rainfall against rooftops has accompanied human life for thousands of years. Farmers depended on it. Forests grew because of it. Entire civilizations survived because clouds drifted overhead, carrying fresh water from one region to another. Even the sound of rain feels gentle to us, predictable, rhythmic, safe. Of course, Earth occasionally produces less friendly versions. Thunderstorms flood streets, hail damages rooftops, freezing rain turns roads into accidental ice skating experiments nobody asked for. Still, beneath all those variations, rain on Earth remains fundamentally familiar. Water condenses in the atmosphere. Droplets form. Gravity pulls them downward. Simple. HD 189733b looked at this concept and decided to become deeply unreasonable about it. Because on this planet, the rain is not water, it is glass. And somehow, even that statement does not fully communicate how horrifying the actual weather may be. The phrase glass rain became one of the most famous details associated with HD 189733b because it perfectly captures the strange balance between science and nightmare that exoplanets often produce. It sounds dramatic enough for science fiction, but astronomers are not inventing it for entertainment value. The underlying chemistry really does suggest conditions where silicate particles condense and move through the atmosphere like rain. The important thing to understand is that glass itself is not some exotic, magical substance. Glass on Earth is largely made from silicates, materials rich in silicon and oxygen. Sand contains silicate minerals. Quartz contains silicates. Large portions of Earth's crust are built from similar chemistry. Under ordinary conditions, silicates remain comfortably solid. You walk across them every day, but temperature changes everything, and HD 189733b possesses temperatures so extreme that ordinary assumptions about matter begin collapsing. On the intensely heated day side of the planet, temperatures climb high enough to vaporize silicate materials into the atmosphere. Imagine heating rock until components of it become vapor drifting through the sky. That alone already feels slightly unreasonable, but then atmospheric circulation carries those vaporized materials toward cooler regions of the planet. There, some of the silicate compounds may condense into tiny droplets or particles. Essentially, parts of the atmosphere begin producing molten glass rain. Except even that description still sounds too calm, because on Earth, rain falls downward through relatively still air. HD 189733b contains supersonic winds, so the rain likely travels sideways, at thousands of miles per hour. Picture a hurricane made of razor blades accelerated by jet engines. Then increase the temperature until metal begins softening. Closer. Still not quite enough, but closer. Scientists believe the atmospheric conditions on HD 189733b may create one of the most violent precipitation systems ever theorized on any known world. The combination of heat, silicate particles, and extreme winds transforms weather itself into something almost weaponized. And strangely enough, it all emerges from perfectly ordinary physics operating under extraordinary conditions. That is one of the recurring themes of astronomy. The universe rarely breaks physical laws. It simply pushes them far beyond the comfortable range humans evolved to experience. Rain exists because atmospheres transport heat and material. That principle works on Earth. It works on Titan with methane. And it works on HD 189733b with vaporized silicates. The details change dramatically, but the underlying physics remain surprisingly universal. In a way, that makes alien planets feel both stranger and more familiar simultaneously. The same universe producing rainforests on Earth also produces sideways glass storms elsewhere. One set of physical laws, infinite possible outcomes. What makes the glass rain especially fascinating is that scientists did not observe literal droplets directly. No telescope currently captures cinematic footage of glass storms sweeping across the planet. Instead, researchers infer these conditions from atmospheric chemistry, temperature profiles, cloud formation models, and spectroscopic observations. Again, astronomy becomes an exercise in reconstruction. Scientists gather clues carefully. Temperature data suggests silicate vaporization. Atmospheric models predict condensation regions. Spectral analysis indicates the presence of relevant compounds, and gradually the picture emerges. An alien world where molten glass likely condenses and races sideways through the atmosphere beneath blue skies. There is something almost surreal about how calmly science phrases these conclusions sometimes. Researchers will publish sentences like, "Silicate condensates may precipitate in the upper atmosphere," which sounds wonderfully professional and controlled. Translated into ordinary language, however, it essentially means the planet appears to be throwing molten glass sideways through a superheated hurricane. The universe occasionally deserves more dramatic wording than scientists usually allow themselves. Of course, the precise nature of the glass rain depends heavily on altitude, temperature gradients, pressure conditions, and atmospheric circulation. Different atmospheric layers likely behave differently. In some regions, silicates remain vaporized. In others, particles condense temporarily. Certain layers may contain cloud-like hazes. Others may produce heavier precipitation. Gas giants are enormously complex atmospheric systems. Even Jupiter and Saturn, relatively close and well studied, still contain mysteries regarding cloud structures and deep atmospheric circulation. HD1897333b is vastly farther away and vastly more extreme, so scientists continuously refine their models as better observations become available. Still, even conservative interpretations remain astonishing and deeply violent. One especially strange aspect of the rain is the direction itself. Human intuition strongly associates rain with downward motion because gravity dominates our experience. Wind may tilt rainfall slightly during storms, but generally precipitation still falls toward the ground. On HD 189733b, however, the winds may become powerful enough to overwhelm that intuitive picture almost entirely. Instead of drifting downward gently, particles could blast laterally through the atmosphere at incredible speeds. This matters because motion changes everything about how the rain behaves physically. Ordinary raindrops striking your skin feel soft because they are small water droplets moving relatively slowly. Tiny silicate particles moving at supersonic speeds would behave more like industrial cutting material. The atmosphere itself becomes erosive, violent, relentless. If any solid object somehow existed within those atmospheric layers, the continuous bombardment would likely strip and damage surfaces aggressively over time. Fortunately for human explorers, no one currently plans vacations there. Though somewhere, statistically speaking, there is probably at least one billionaire looking at the planet and saying, "Interesting investment opportunity." One fascinating question astronomers sometimes explore involves whether any truly stable atmospheric regions exist on worlds like HD 189733b. Gas giants do not possess solid surfaces the way Earth does, but atmospheric pressure and temperature vary enormously with depth. Could there be layers where conditions become less catastrophic? Possibly in relative terms, but less catastrophic on HD 189733b still remains deeply unpleasant by Earth standards. The atmosphere overall exists under such intense stellar heating and dynamic circulation that calm conditions appear unlikely across large regions, and deeper atmospheric layers introduce crushing pressures alongside rising temperatures. The deeper you descend, the worse things generally become. Gas giants are remarkably unfriendly that way. Jupiter itself contains atmospheric pressures so enormous deep below the cloud tops that hydrogen may transition into metallic states. The physics occurring there becomes almost difficult to imagine because Earth contains nothing comparable naturally. HD 189733b likely contains similarly bizarre deep atmosphere conditions amplified by far greater heating from its nearby star. Which means the famous glass rain probably represents only the beginning of the planet's atmospheric absurdity. Another interesting aspect involves cloud formation itself. Clouds on Earth appear soft and comforting largely because they consist of tiny suspended water droplets or ice crystals. Sunlight passing through them creates beautiful colours and gentle lighting. clouds on HD 189733b may contain entirely different materials: silicate haze, condensed mineral particles, exotic compounds shaped by extreme chemistry. And yet, from far away, they still create beauty. That contrast keeps appearing repeatedly with this planet. Violence wrapped in elegance, danger disguised as serenity, aesthetic calmness masking atmospheric chaos. It almost feels symbolic somehow, though the universe itself probably does not intend symbolism. Humans simply enjoy finding meaning in dramatic things. Still, there is something emotionally fascinating about a world that looks so peaceful while being fundamentally unlivable. Earth's atmosphere protects life gently. It regulates temperature, distributes water, blocks harmful radiation, and creates breathable air. HD 189733b's atmosphere behaves more like a gigantic cosmic blender. Same broad concept, very different personality. Astronomers studying exoplanets often discuss habitability carefully, because the term involves much more than simply existing within a certain temperature range. Atmospheric chemistry matters enormously. Stellar radiation matters. Pressure stability matters. Magnetic fields matter. A planet can look visually stunning while remaining utterly hostile to biology. HD 189733b demonstrates that beautifully, and perhaps slightly menacingly. Interestingly, the public fascination with glass rain reveals something important about how humans emotionally connect to astronomy. People love specifics. A giant hot gas planet sounds abstract. A world where it rains sideways molten glass instantly becomes memorable. Concrete details anchor imagination. We cannot emotionally picture high-temperature silicate condensation dynamics easily. But we can picture sharp rain cutting through darkness beneath blue alien skies. The universe becomes emotionally real through details, and exoplanets provide extraordinary details. As telescope technology improves, scientists expect to discover even stranger atmospheric phenomena elsewhere. There may be worlds with mineral snow, planets where metals condense into droplets, atmospheres rich in hydrocarbons producing bizarre organic haze, extreme winds interacting with magnetic fields, entire climate systems unlike anything in our solar system. Humanity has only just begun exploring the true diversity of planetary environments, and already the universe appears dramatically more creative than expected. For centuries, humans wondered whether other worlds existed. Now we know they do, and apparently some of them contain horizontal glass hurricanes beneath cobalt skies. Reality really has become increasingly ambitious lately. One especially unsettling detail about the glass rain is imagining its sound, or rather, the impossibility of imagining it properly. Earth rain creates soft tapping sounds because of water droplets interacting with surfaces and air. But HD 189733b likely contains roaring atmospheric shockwaves, violent turbulence, and high-speed particle collisions across enormous scales. If a human somehow survived briefly inside the upper atmosphere, which they absolutely would not, the sound environment alone would probably be catastrophic. Continuous supersonic turbulence, screaming winds, shock interactions, possibly electrical activity within clouds. The atmosphere may resemble an endless industrial catastrophe stretching across an entire planet. And yet, from 64 light-years away, all of that compresses into a beautiful blue point drifting silently through darkness. That contrast never really stops being astonishing. There is also something strangely humbling about the realization that weather itself can become so extreme elsewhere. Humans often think of Earth as dramatic because Earth is the only environment we know personally. Our storms feel enormous to us. Our climate shapes civilization. But exoplanets keep reminding us that Earth exists within a surprisingly narrow and gentle slice of possibility. The universe allows conditions far beyond human intuition. Worlds where rain becomes glass, worlds where skies glow with vaporized rock, worlds where the atmosphere itself moves faster than sound, and HD 189733b is merely one example among thousands already discovered, which naturally raises another question. If the weather is already this violent in the upper atmosphere, what would it actually feel like to experience the planet directly? Suppose, just for a moment, that impossible engineering somehow became possible. Suppose humanity built a spacecraft capable of surviving temperatures hotter than molten lava, pressures beyond comprehension, radiation intense enough to damage ordinary electronics, and winds moving faster than sound itself. Suppose that spacecraft crossed 64 light-years of darkness and arrived safely beside HD 189733b. And suppose, against every reasonable survival instinct in the universe, someone decided to descend into the atmosphere. What would they actually experience? The answer is difficult to describe because nearly every part of the environment violates ordinary human intuition. We evolved beneath calm gravity, moderate air pressure, breathable oxygen, and weather systems gentle enough that rain occasionally becomes associated with romance instead of immediate disintegration. HD 189733b belongs to an entirely different category of existence. And one of the strangest things about imagining the planet is realizing that there may never be a moment where you truly arrive anywhere. Because gas giants do not possess ordinary surfaces, Earth gives us comforting boundaries. Sky above, ground below, stand here, walk there. Even oceans eventually end at shorelines. But worlds like HD 189733b dissolve those familiar distinctions entirely. If you descended into the atmosphere, there would be no solid ground waiting beneath the clouds. The atmosphere would simply grow denser and hotter and more pressurized the deeper you traveled. It would feel less like entering weather and more like sinking into an endless planetary ocean made of gas, heat, and pressure. And all around you, the storm would continue, forever. That is perhaps the most psychologically unsettling part. Earth storms end. Even the worst hurricane eventually weakens. Tornadoes dissipate. Thunderstorms move on. Human beings understand weather partly because weather changes. But HD 189733b may exist in a state of near-permanent atmospheric violence. There are no calm, blue mornings after the storm passes. The storm is the climate. The storm is the world. From high above the atmosphere, the planet might still appear deceptively peaceful. Smooth blue coloration, gentle gradients of light, elegant curves against the darkness of space. But the moment you began descending, that illusion would collapse rapidly. The upper atmosphere itself would already be hostile far beyond human tolerance. Temperatures would rise quickly. Pressure would increase. Hydrogen and helium gases would surround you beneath haze layers filled with silicate particles. And then the winds would begin making themselves known. On Earth, strong wind presses against your body in a way that feels familiar. You lean slightly into it while walking. Your clothes ripple. Trees bend. Perhaps your umbrella launches into a neighbouring county. Human beings can still function inside ordinary wind because Earth's atmosphere remains relatively thin and slow-moving compared to the nightmare unfolding on HD 189733b. There, the atmosphere itself moves at several thousand miles per hour. The difference is almost impossible to internalise emotionally because human brains are not built to comprehend air behaving that violently. Imagine sitting inside a commercial airplane during takeoff. The engines roar. Acceleration pushes you gently backward. Outside, the air rushes past at hundreds of miles per hour. Now, imagine that speed multiplied enormously until the surrounding atmosphere itself becomes a continuous shockwave. And then imagine floating inside it. You would not experience wind in the Earth sense anymore. You would experience atmospheric force. The movement of matter itself transformed into something overwhelming and relentless. Any exposed object would endure continuous bombardment by high-speed particles, and among those particles, according to current models, would likely be molten silicates condensing into microscopic shards and droplets, the famous glass rain. Except from inside the storm, the word rain would probably stop feeling appropriate. Rain suggests direction, comfort, pattern. This would resemble an endless horizontal blast furnace loaded with razor-edged debris, and because the atmosphere lacks a clear solid surface, the storm would not feel geographically contained. No mountains to shelter behind, no caves, no stable land, only deeper atmospheric layers waiting below. The deeper you descended, the more extreme conditions would become. Pressure inside gas giants increases enormously with depth because the weight of the atmosphere above becomes crushing. Even Jupiter, which receives far less stellar heating than HD 189733b, contains pressure environments so intense that hydrogen may transition into exotic metallic states. HD 189733b combines giant planet gravity with extreme stellar heating. Its atmospheric physics likely become astonishingly violent deeper down. Eventually, temperatures and pressures would overwhelm almost any imaginable spacecraft design. Structures would compress, materials would fail, electronics would collapse. The atmosphere itself would gradually become less like weather and more like a hostile planetary interior. One strange thing about gas giants is that they blur the line between atmosphere and planet entirely. On Earth, we separate weather from geology naturally. The atmosphere exists above the planet, but on a gas giant, the atmosphere is the planet. Clouds transition downward into denser layers. Pressure rises continuously. Chemistry changes with depth. There is no obvious dividing line where sky ends, so imagining life inside the storm becomes psychologically disorienting because there is no stable frame of reference, no horizon, no land, no familiar geography, only movement, heat, pressure, and endless atmospheric violence. Scientists believe the planet is tidally locked, meaning one side always faces the star while the opposite side remains in permanent darkness. This creates enormous thermal contrasts driving the supersonic winds across the globe. If you somehow floated within the atmosphere long enough to move between hemispheres, you might witness gradual transitions between infernal daylight and endless night. But even the night side would not provide peace. Heat transported by atmospheric circulation still keeps temperatures extremely high, and the winds themselves remain globally interconnected. The atmosphere never truly rests. One especially eerie idea involves the possibility of enormous lightning systems within the clouds. Astronomers suspect electrical activity may occur in many giant planetary atmospheres. Jupiter and Saturn both produce powerful lightning storms. Given the turbulence, particle collisions, and energetic atmospheric dynamics on HD 189733b, giant electrical discharges may be possible there too. Imagine flashes of light illuminating endless blue-black storm clouds, while molten silicate particles race sideways through supersonic winds. It sounds cinematic because reality occasionally behaves like a science fiction director, with absolutely no restraint. And yet, despite all this violence, the atmosphere still obeys ordinary physical laws. That may be the strangest part. Nothing supernatural is happening, no magical forces, no fictional physics, only heat, pressure, radiation, chemistry and fluid dynamics pushed to extremes humans never evolved to witness. The universe does not need fantasy to create terrifying worlds. Reality already seems perfectly capable on its own. Interestingly, some scientists speculate about whether there could be atmospheric layers within giant planets, generally where conditions become temporarily less extreme. Not comfortable, certainly, but perhaps comparatively moderate relative to the surrounding chaos. On Jupiter and Saturn, for example, pressure and temperature conditions vary significantly with altitude. Certain cloud layers contain more stable chemistry than others. Carl Sagan once speculated imaginatively about hypothetical floating life forms in giant planetary atmospheres, though entirely speculative and unsupported by evidence. HD 189733b, however, likely pushes environmental violence too far for anything remotely Earth-like biologically. Temperatures remain extraordinarily high, radiation exposure is severe, atmospheric dynamics appear relentless. The planet feels less like a place where life might adapt and more like a demonstration of how hostile planets can become, and yet humans remain fascinated by it, perhaps because there is something deeply compelling about extreme environments. People watch documentaries about volcanoes, deep oceans, tornadoes, and polar blizzards for similar reasons. Dangerous places reveal the raw power of nature more clearly than comfortable environments do. HD 189733b simply magnifies that fascination to planetary scales. A world where weather itself becomes monstrous. Another strange aspect of imagining the storm involves time perception. Earth weather unfolds in cycles humans understand. Storms build gradually, peak, then fade. We measure weather through beginnings and endings, but on HD 189733b, the atmospheric engine likely operates continuously over enormous spans of time. The planet has probably endured these conditions for millions or even billions of years. Imagine a hurricane lasting longer than human civilization. That is closer to the scale involved. The atmosphere may shift and fluctuate dynamically, of course, but the overall violent state remains persistent because the underlying energy imbalance never disappears. The star keeps heating one side relentlessly. The atmosphere keeps trying to redistribute that energy. The winds keep roaring. The glass keeps falling sideways, forever, or close enough that the distinction stops mattering emotionally. This creates a strangely haunting image. An eternal storm beneath blue skies. No seasons, no peaceful intervals, no calm after the weather breaks. Only continuous atmospheric motion circling a giant alien world. And somewhere inside all that violence, chemistry continues unfolding automatically according to physical laws indifferent to human ideas about comfort. There is also something oddly humbling about realizing how fragile human beings actually are compared to planetary environments. Earth protects us so thoroughly that we often forget how narrow our survival window truly is. Small changes in oxygen concentration, temperature, pressure, or radiation exposure become dangerous surprisingly quickly. Space itself remains lethal almost everywhere. HD 189733b reminds us that even planets can be profoundly hostile. Not all worlds are waiting to be explored peacefully. Some are simply too extreme, too energetic, too violent. And maybe that is important to remember. Science fiction often portrays humans eventually spreading comfortably across the galaxy, adapting everywhere with enough technology. But reality may impose harsher limits. Certain worlds may remain permanently inaccessible except through observation, places humanity can study but never truly visit. HD 189733b feels like one of those places, a planet that almost exists as pure atmosphere and force, and yet, even if no human ever reaches it physically, we already know astonishing amounts about it. Its orbit. Its mass, its atmospheric chemistry, its winds, its colour, its weather. Tiny creatures on a rocky world somehow learned how to read the climate of an alien planet across interstellar distances. That remains extraordinary no matter how often astronomy achieves impossible things. The deeper scientists study exoplanets, the more the galaxy transforms from an abstract collection of stars into a place filled with actual worlds. Not merely points of light, worlds, storms, skies, clouds, heat, motion, and HD 189733b became one of the clearest reminders that the universe contains environments far beyond anything Earth prepared us to imagine comfortably. There is a side of the moon you never see, not because it is hidden deliberately and not because the moon rotates strangely, but because it rotates in exactly the right way. As the moon orbits Earth, it also spins slowly on its axis. The timing matches so perfectly that one hemisphere always faces us while the opposite side remains permanently turned away. For most of human history, humans never knew what the far side looked like at all. Ancient civilizations gazed upward for thousands of years without ever seeing half the moon. That alone is strangely comforting somehow. Even familiar things can keep secrets for a very long time. The process responsible for this arrangement is called tidal locking, and throughout the universe it appears surprisingly common. Moons become tidally locked to planets. Planets become tidally locked to stars. Gravity pulls constantly on worlds, stretching them slightly, distorting them over immense periods of time until rotation gradually synchronizes with orbit. Eventually the same face always points toward the object being orbited, and on HD 189733b, tidal locking changes absolutely everything. Without it, the planet would still be extreme. It would still be dangerously hot because of its close orbit around its star. The atmosphere would still contain violent chemistry and massive storms, but tidal locking transforms ordinary extremity into something much stranger, because one side of the planet lives beneath endless daylight, and the other side never sees the star at all. Imagine that for a moment. No sunrise, no sunset, no dawn gradually brightening the horizon, no evening shadows stretching across landscapes. One hemisphere burns beneath permanent stellar radiation, while the opposite side remains trapped in eternal night. Earth's entire biological history evolved around cycles of light and darkness. Morning and evening shaped animal behavior, migration patterns, sleep cycles, plant growth, even human emotion. Our brains still carry ancient responses to sunlight. Morning light tells the body to wake. Darkness signals rest. Entire cultures organize themselves around the movement of the sun across the sky. But on HD 189733b, the sky never changes, at least not in that familiar way. If you somehow hovered above the dayside atmosphere, the star would remain fixed overhead continuously, glaring down through layers of superheated clouds and silicate haze. No relief, no cooling night, just endless radiation pouring into the atmosphere every second. Meanwhile, on the night side, the star never rises at all. The atmosphere there exists beneath perpetual darkness, interrupted only by whatever dim glow and thermal radiation the planet itself produces. This permanent imbalance drives the weather systems we discussed earlier. The day side absorbs enormous energy while the night side remains comparatively cooler, and the atmosphere responds by trying constantly to redistribute heat across the planet. That redistribution becomes violent enough to generate the famous supersonic winds. In many ways, tidal locking is the true engine behind the planet's madness. Without tidal locking, the atmosphere would heat and cool more evenly as the planet rotated. But because one hemisphere remains permanently exposed, the atmosphere never reaches equilibrium. The storm never truly settles. It simply circulates endlessly around the world. Scientists believe HD 189733b became tidally locked because it orbits incredibly close to its star. The closer a planet lies to a massive object, the stronger tidal forces become. And this planet is astonishingly close. It completes a full orbit in just over 2 Earth days. Imagine Earth orbiting so close to the Sun that an entire year lasted only a weekend. At that distance, gravity exerts tremendous influence over the planet's rotation. Over time, tidal forces slowed and synchronized the planet until one hemisphere permanently faced the star. This process likely took millions of years, perhaps less given the extreme proximity involved. Astronomically speaking, that is fairly quick. The result is a world split permanently into 2 atmospheric realities. The day side becomes brutally hot under constant stellar irradiation. Temperatures soar high enough to vaporize silicates and drive enormous atmospheric expansion. Energy pours continuously into the atmosphere without interruption. Meanwhile, the night side loses heat into space beneath endless darkness. Not enough to become cold by Earth standards certainly, but cooler relative to the infernal dayside. And between those two hemispheres, the atmosphere races furiously in an attempt to balance impossible conditions. Earth experiences temperature differences too, of course. Deserts become hot during the day and cool at night. Polar regions remain colder than the tropics. Seasonal shifts redistribute sunlight differently across hemispheres. But Earth rotates every 24 hours, preventing any one region from enduring eternal noon or endless midnight. That rotation stabilizes climate enormously. HD 189733b lacks that stabilizing cycle. Its climate is essentially trapped inside one permanent weather pattern. One especially strange consequence of tidal locking involves the location of the hottest atmospheric region. Scientists expected the point directly beneath the star to be hottest because it receives the most radiation. But observations revealed that the hottest region appears shifted eastward. Why? Because the winds are so powerful that they physically drag heat across the atmosphere before it can radiate away. Imagine weather systems so extreme they pull the hottest part of the atmosphere sideways around the planet. Again, the scale becomes difficult to visualize comfortably. On Earth, atmospheric circulation influences climate strongly, but sunlight still generally defines the warmest regions predictably. HD 189733b's atmosphere becomes dynamic enough to distort even that expectation. The entire planet behaves like a gigantic thermal machine struggling continuously against imbalance, and the star itself never stops feeding energy into the system. There is something psychologically unsettling about eternal daylight specifically. Humans often romanticize endless sunshine until they think about it carefully. Daylight feels positive partly because it contrasts with darkness. Morning feels refreshing because night existed beforehand. Without cycles, even pleasant things become exhausting. Researchers studying human behavior in polar regions already understand how strongly continuous light or darkness affects psychology. People living through polar summers or winters sometimes experience disrupted sleep, mood changes, and altered circadian rhythms because the natural day-night cycle weakens. Now imagine an entire planet where the sky literally never changes. No clocks needed. No evening arriving naturally. No stars appearing overhead on the day side ever. Only relentless brightness. Of course, no humans stand there to experience psychological consequences, but imagining the environment still feels eerie because our brains instinctively expect skies to move. Earth taught us that. The sun rises, the sun sets, time passes visibly overhead. On HD 189733b, time becomes strangely frozen in the sky itself, and the night side may feel equally unsettling in the opposite direction. Perpetual darkness carries its own emotional weight. Humans evolved fearing darkness partly because predators hid within it historically. Even today, endless darkness feels psychologically heavy after long periods. But on HD 189733b, the night-side darkness would not resemble peaceful nighttime on Earth. The atmosphere itself remains violently active. Heat from the dayside still pours across the planet through atmospheric circulation. Winds roar endlessly through dark cloud systems while glass particles race through the atmosphere. It would not feel quiet, only dark. Dark and violent. One interesting question scientists ask about tidally locked exoplanets generally is whether the boundary region between day and night sides, sometimes called the terminator zone, could host somewhat more moderate conditions. On certain rocky exoplanets orbiting red dwarf stars, researchers speculate that tidal locking might create habitable regions near this twilight boundary where temperatures remain less extreme. But HD 189733b is far too hot overall for such optimism. Its atmosphere remains extreme across the entire globe. Still, the terminator region likely plays a crucial role in atmospheric dynamics because it represents the transition between constant heating and continuous cooling. Immense pressure differences and temperature gradients emerge there. The atmosphere likely becomes especially turbulent in those regions as hot gases surge toward cooler zones. The planet essentially contains a permanent battle line between fire and darkness, and the weather is born from that conflict. Another fascinating consequence of tidal locking involves cloud formation and chemistry. On Earth, sunlight cycles influence atmospheric temperatures continuously. Clouds form and dissipate depending on local heating conditions. On HD 189733b, however, cloud behavior may become more geographically fixed. Certain materials may condense preferentially on cooler regions while remaining vaporized elsewhere. Atmospheric chemistry becomes spatially organized according to permanent stellar exposure. In other words, entire weather systems may remain locked into place globally. Earth weather migrates. HD 189733b weather circulates endlessly within fixed hemispheric roles. And because the planet orbits so close to its star, tidal locking probably influences more than just atmospheric behavior. The star's gravity may stretch the planet slightly, creating tidal distortion throughout its structure. Similar effects occur between Earth and the Moon, where tidal forces raise ocean tides daily. But HD 189733b experiences vastly stronger gravitational interactions because of its close orbit and giant size. The planet may not even be perfectly spherical anymore. It could be subtly elongated by stellar gravity. The universe really does enjoy taking ordinary concepts and pushing them toward absurdity. Earth experiences tides. HD 189733b experiences permanent planetary distortion beneath endless glass storms. Same principle, very different outcome. Astronomers are especially interested in tidally locked planets because many potentially habitable exoplanets around red dwarf stars may also become tidally locked due to close orbits. Red dwarfs are smaller and cooler than our Sun, meaning habitable zones lie much closer to the star itself. Planets orbiting there often become gravitationally synchronized over time. This raised concerns initially because scientists worried tidal locking might automatically make planets uninhabitable. One side burning, one side frozen, atmospheric collapse possible. But later climate models suggested atmospheres and oceans might redistribute heat effectively enough to support stable environments under certain conditions. HD 189733b, however, demonstrates the more extreme end of tidal locking outcomes. Its proximity to the star pushes atmospheric circulation into violent territory, and because it is a gas giant rather than a rocky world, the weather becomes even more chaotic. Still, despite everything we know about this planet's terrifying atmosphere, it remains oddly beautiful conceptually. A world divided permanently between fire and darkness, blue skies filled with molten glass, supersonic winds wrapping endlessly around the globe. There is something almost mythological about it. Ancient cultures often imagined cosmic realms split between opposing forces. Eternal daylight and eternal night feel like concepts from old legends rather than astrophysics papers, and yet here it is, real. Orbiting quietly around a distant star while humanity watches from far away through telescopes. One especially humbling realization about tidally locked worlds is how much planetary identity depends on orbital mechanics. Tiny differences in distance, mass, rotation, and gravitational interaction can completely reshape a world's destiny. Earth avoided tidal locking partly because of its distance from the Sun and its rotational history. HD 189733b did not, and that single difference transformed the planet into one of the most violent weather systems ever discovered. The atmosphere we have been discussing exists because the sky itself stopped changing. The star remains fixed overhead. The heating never ends. The cooling never balances completely. And so the planet continues circling its star beneath permanent atmospheric chaos. But if one side of HD 189733b lives beneath endless daylight, while the other remains trapped in eternal darkness, what exactly would those two hemispheres look like up close? On Earth, no place escapes the turning of the planet forever. Even the longest day eventually fades. Even the darkest night eventually breaks. The rotation of Earth creates rhythm so naturally that most of us rarely think about it. Morning arrives, afternoon drifts by, evening settles quietly over cities and forests. Then darkness comes, bringing cooler air, stars and rest before the cycle begins again. Human civilization built itself around that rhythm. Farmers planted by it. Sailors navigated beneath it. Religions, calendars, holidays and sleep itself all became tied to the steady turning of Earth beneath the sun. But HD 189733b abandoned that rhythm long ago. One side of the planet faces the star permanently, the other never sees it at all. And between those two hemispheres exists one of the strangest environmental contrasts in the known universe. The day side of HD 189733b is a world of endless exposure. The star hangs fixed overhead continuously, pouring radiation into the atmosphere without interruption. There is no sunset to cool the clouds, no nighttime recovery, no pause in heating. The sky itself may glow with intense blue haze scattered through superheated atmospheric layers. Beneath that haze, temperatures climb high enough to vaporize silicates and distort atmospheric chemistry into something utterly alien compared to Earth. And yet the really strange thing is that despite all this violence, the day side might still appear visually magnificent from a safe enough distance. Human beings are oddly drawn to extremes. Volcanoes erupt beautifully from orbit. Lightning storms look spectacular across nighttime continents. Even dangerous things can appear serene when viewed from afar. HD 189733b's dayside likely belongs firmly in that category. A glowing blue inferno wrapped around a giant planet larger than Jupiter. One eternal afternoon stretched across an entire hemisphere. The temperatures there are difficult to grasp emotionally because Earth contains almost nothing comparable outside industrial furnaces and volcanic interiors. Some regions may exceed 1000 degrees Celsius. That is hot enough to melt many metals. Hot enough that ordinary rock chemistry begins changing behaviour entirely. Hot enough that atmospheric gases themselves become chemically restless and unstable. Earth deserts feel brutally hot to humans because our bodies evolved within narrow thermal limits. Even temperatures around 50 degrees Celsius can become life-threatening quickly. HD 189733b exceeds those conditions so dramatically that ordinary human comparisons start breaking down. You would not feel warm there. You would stop existing in any recognizable biological sense almost immediately. Even spacecraft would struggle enormously, and still the star keeps shining endlessly overhead. One especially eerie aspect of the day side involves shadows. On Earth, shadows move naturally throughout the day as the sun crosses the sky. Morning shadows stretch long toward the west. Noon compresses them tightly beneath objects. Evening sends them drifting eastward. Movement gives shadows personality somehow. But on HD 189733b, the star never moves. Any shadows would remain fixed permanently according to local atmospheric conditions. Imagine a world where the sky itself appears frozen in time. No sunrise, no afternoon, no evening. Only continuous illumination beneath violent atmospheric turbulence. The atmosphere likely glows with thermal radiation as well because of the immense heat involved. Clouds and haze layers may shimmer strangely depending on temperature and chemical composition. Astronomers suspect the atmosphere absorbs stellar energy efficiently, creating enormous thermal gradients across different altitudes. Everything about the day side feels energetically overloaded. The night side, meanwhile, belongs to an entirely different reality. No direct starlight reaches it. Ever. The star remains permanently below the horizon, if a gas giant can even meaningfully be said to possess a horizon in the familiar sense. And unlike Earth's night side, which cools temporarily before dawn arrives again, HD 189733b's dark hemisphere exists in endless cosmic midnight. But calling it cold would still be misleading. This is not a frozen world. The atmosphere transports enormous amounts of heat from the day side continuously through those supersonic winds. Temperatures on the night side remain extremely high by Earth standards, even without direct stellar exposure. In some ways, the night side may feel even stranger than the day side precisely because it combines darkness with heat. Human intuition associates darkness with cooling naturally. Nightfall on Earth usually brings relief from daytime heat. Deserts become cold after sunset because solar heating disappears rapidly. But on HD 189733b, the atmosphere itself carries heat aggressively across the planet. Even eternal darkness cannot fully overcome the atmospheric engine roaring through the world. Imagine standing inside a furnace room after someone turned off the lights. That might emotionally approximate the night side better than ordinary nighttime imagery. Scientists believe the atmosphere likely redistributes energy so efficiently that the temperature difference between day and night sides, while enormous, is smaller than early models once predicted. That discovery itself became important because it confirmed how violently the atmosphere moves heat around the planet. Without those winds, the day side would become even hotter while the night side cooled much more dramatically. Instead, the atmosphere acts like a gigantic conveyor belt transporting thermal energy continuously. And because the night side remains hidden from direct observation more often, much of its behaviour still involves active scientific modelling and interpretation. Astronomers study infrared emissions carefully to estimate atmospheric conditions there. By measuring thermal radiation during different orbital phases, researchers gradually reconstruct temperature distributions across the globe. Again, humanity somehow learned how to map heat patterns on a world 64 light-years away. That achievement never really stops being extraordinary. One especially fascinating possibility involves cloud differences between hemispheres. The cooler night side may allow different materials to condense compared to the blazing day side. Atmospheric chemistry could vary significantly depending on local temperature and circulation patterns. Perhaps thicker cloud layers form in certain dark regions. Perhaps silicate condensation becomes more prominent there before winds carry material back toward hotter zones. The entire atmosphere may behave like a giant planetary recycling system, driven by permanent imbalance. Material vaporizes on the day side, winds transport it, cooling triggers condensation elsewhere, then circulation repeats endlessly. A weather cycle powered by eternal day and endless night. And somewhere within those atmospheric currents, the famous glass rain continues moving sideways through the darkness. There is also something psychologically strange about imagining eternal darkness specifically. Humans evolved under stars, but always with the expectation that morning would return eventually. Night on Earth feels temporary. Even the longest winter nights eventually end. But the night side of HD 189733b has no dawn. No warm horizon gradually brightening. No birds announcing sunrise. Only permanent atmospheric turbulence beneath unseen skies. If an observer somehow floated within the night-side atmosphere, the visual environment might become deeply alien. Perhaps dimly glowing clouds lit by thermal radiation, flashes of lightning within storm systems, heat shimmering invisibly through darkness, winds roaring continuously beyond comprehension. The atmosphere itself may emit faint infrared glow because of its temperature, though human eyes would struggle to perceive much of it directly. It would not resemble peaceful nighttime on Earth, more like the interior of a giant cosmic machine still running in the dark, and somewhere beyond the horizon, permanently unreachable, the star would continue blazing over the day side. One world divided into two incompatible experiences, fire and darkness separated by storms. Interestingly, astronomers often discuss the terminator zone on tidally locked planets, the boundary between day and night hemispheres, where stellar illumination transitions continuously into darkness. On Earth, The Terminator moves across the globe constantly during sunrise and sunset. On HD 189733b, however, the Terminator remains geographically fixed. One permanent twilight ring circling the planet. That region may host some of the most chaotic atmospheric behaviour anywhere on the world because it represents the collision between extreme heating and continuous cooling. Supersonic winds likely race through those boundary regions carrying heat, material, and momentum between hemispheres. If any area of the planet visually resembled a science fiction storm world most strongly, it might be there. Perpetual twilight beneath roaring atmospheric currents, blue haze merging into darkness, heat and night colliding endlessly. The universe occasionally creates environments that sound almost too cinematic to be real, yet HD 189733b simply exists quietly according to ordinary physics. Gravity, radiation, fluid dynamics, nothing magical required. One fascinating implication of tidal locking involves how completely it reshapes planetary identity. Earth's continents, climates, and ecosystems depend profoundly on rotation. Without Earth's day-night cycle, weather systems would reorganize dramatically. Oceans would circulate differently. Temperatures would redistribute in unfamiliar ways. Life itself might have evolved entirely differently. HD 189733b demonstrates just how powerful orbital mechanics become over planetary timescales. The entire atmosphere exists in its current violent state largely because the sky stopped changing. And the more scientists study tidally locked exoplanets, the more important those worlds become for understanding planetary diversity generally. Many planets orbiting red dwarf stars may also become tidally locked, because habitable zones around smaller stars lie much closer inward. Some of those worlds might still support atmospheres or even oceans under the right conditions. HD 189733b represents an extreme example rather than a typical one, but it helps scientists understand how atmospheres behave when exposed to permanent hemispheric imbalance. Extreme worlds often teach the clearest lessons, and perhaps there is something strangely beautiful about that division between eternal day and endless night. Not beautiful in a comfortable Earth sense, more in the sense that cosmic systems often produce elegant outcomes from simple physical rules. A planet orbits too close to its star. Gravity synchronizes rotation. One side receives endless light. The atmosphere begins moving heat. Storms emerge. Glass condenses. Supersonic winds circle the globe. And suddenly an entire alien world exists unlike anything human beings imagined for most of history. All because gravity kept turning the same face toward the star. Human beings have a remarkable habit of imagining themselves everywhere. We picture standing on Mars beside dusty cliffs. We imagine floating through the clouds of Jupiter. Science fiction has filled entire libraries with astronauts walking across alien landscapes, building colonies beneath strange skies, and planting flags in places evolution never intended us to survive. Part of that instinct comes from curiosity, part comes from optimism, and part comes from the fact that humans consistently underestimate how fragile they actually are. Earth protects us so completely that we forget how narrow our survival window truly is. A small drop in oxygen becomes dangerous. A modest increase in radiation becomes harmful. Water pressure crushes us surprisingly quickly beneath the oceans. Even ordinary cold or heat can kill without shelter. Space itself is hostile almost everywhere. HD 189733b takes that hostility and escalates it into something bordering on absurd. Still, it is difficult to look at an alien world without wondering the same question eventually. What would actually happen if a human visited it? The short answer is that you would die. Very quickly, very dramatically, and probably in several different ways at once. But the longer answer is much more interesting because it reveals just how extreme the planet truly is. First, there is the obvious problem of distance. HD 189733b lies about 64 light-years away from Earth. Light itself takes 64 years to cross that gap, travelling at roughly 300,000 kilometres per second. Modern spacecraft are nowhere remotely close to that speed. Voyager 1, one of the fastest human-made objects ever launched, travels around 17 kilometres per second relative to the Sun. At that speed, reaching HD 189733b would require well over 1 million years. Human civilization itself is younger than that by quite a large margin, so before anyone even arrives at the planet, we already encounter the first great reality of interstellar travel. The universe is enormous, painfully enormous. Science fiction often compresses space for storytelling convenience, because otherwise entire movies would involve characters spending 700 years quietly waiting inside a spaceship while arguing about maintenance schedules. Reality is less cooperative. Still, suppose somehow humanity solved interstellar travel. Suppose an advanced civilization eventually built ships capable of crossing light years within human timescales. Maybe through relativistic travel, suspended animation, generation ships, or technologies not yet imagined. Eventually, after crossing unimaginable darkness, the planet would appear ahead. At first, probably beautiful, blue, glowing softly beside its orange star. Perhaps even peaceful from far away. That illusion would not survive long. Even approaching the planet safely would become difficult because HD 189733b orbits extremely close to its star. The region around the planet experiences intense radiation and powerful stellar activity. Electronics would require extraordinary shielding simply to operate reliably nearby. Then comes the atmosphere. Earth's atmosphere is gentle enough that humans barely notice its existence most of the time. We move through it continuously without thinking. Wind feels normal. Breathing feels automatic. HD 189733b's atmosphere would feel less like air and more like a planetary weapon system. Suppose a spacecraft entered the upper atmosphere. Immediately, temperatures would begin rising to catastrophic levels. Atmospheric friction alone already poses enormous challenges for spacecraft entering Earth's atmosphere. Engineers spend years designing heat shields capable of surviving a few minutes of controlled descent. Now imagine descending into an atmosphere already hotter than molten lava before friction even becomes relevant. This spacecraft would require absurd thermal protection systems simply to avoid vaporizing, and then the winds would arrive. Not strong winds in the Earth sense, not hurricanes, not tornadoes. Atmospheric flows moving several times faster than the speed of sound. At those velocities, the atmosphere itself exerts extraordinary force. Turbulence would become violent beyond anything ordinary aircraft experience. Pressure waves and shock interactions would hammer the vehicle continuously. Flying through HD 189733b would resemble attempting to steer through an exploding industrial furnace during a perpetual sonic boom, and somewhere within that chaos, tiny silicate particles would streak sideways through the atmosphere. The famous glass rain. Except rain still feels too gentle a word. At those speeds, the particles behave more like high-temperature abrasive projectiles. Even microscopic impacts become dangerous when velocities become extreme enough. Spacecraft surfaces would endure continuous erosion, sensors would struggle, visibility might become terrible depending on atmospheric depth. And the deeper the descent continued, the worse conditions would become. This is where gas giants become especially unsettling. On Earth, no matter how dangerous the weather gets, there is usually still ground somewhere below. Hurricanes end at coastlines. Storms move across landscapes. Humans instinctively imagine escape downward towards stable surfaces. HD 189733b offers no such comfort. There is no ordinary surface waiting beneath the clouds. The atmosphere simply grows denser and hotter with depth. Pressure increases continuously. temperatures rise, the chemistry becomes stranger, and gravity keeps pulling you farther inward. Eventually, the atmospheric pressure would crush almost any conceivable human-scale vehicle. Even submarines designed for Earth's deep oceans struggle against pressures far smaller than those likely found deep within giant planets. Jupiter itself contains pressures millions of times greater than Earth's atmospheric pressure in deeper layers. HD 189733b combines giant planet gravity with enormous stellar heating. Its deeper atmosphere likely becomes a realm of exotic physics, utterly inaccessible to human survival. But suppose somehow a person survived inside a protected vehicle floating in the upper atmosphere temporarily. What would they actually perceive? The sky might glow deep blue through silicate haze. The star would appear fixed permanently in one position overhead if you remained on the day side. Cloud systems would race across the atmosphere with terrifying speed. The motion itself might feel disorienting because human intuition expects skies to move gradually, not violently. Lightning may flash within distant atmospheric layers. The vehicle would shake continuously beneath turbulence, and the sound, or rather, the overwhelming impossibility of sound there. Earth storms already become deafening during hurricanes or severe thunderstorms. Wind howls around structures, thunder shakes windows, now increase atmospheric velocity beyond the speed of sound itself. The atmosphere of HD 189733b likely produces continuous roaring turbulence across planetary scales. Inside a protected vehicle, vibrations alone might become exhausting. Outside, the storm would probably sound less like weather and more like machinery tearing itself apart endlessly. And that storm never ends. That is another detail worth remembering. Earth weather feels survivable partly because it changes. Even terrible storms eventually weaken. HD 189733b exists in a state of near-permanent atmospheric violence, driven by tidal locking and constant stellar heating. The storm is not temporary, the storm is the climate. One especially strange challenge for humans would involve orientation. Without a solid surface or stable horizon, the atmosphere might feel psychologically disorienting very quickly. Human beings evolved around landscapes, trees, mountains, coastlines, buildings. Even pilots rely heavily on stable reference systems. Inside the atmosphere of a gas giant, especially one this turbulent, there may be no meaningful visual stability at all. Only endless clouds, turbulence, and shifting atmospheric layers. The environment would feel less like visiting a planet and more like falling forever through a storm, which in many ways is exactly what it would be. Interestingly, science fiction sometimes portrays giant planets romantically, imagining floating cities drifting peacefully through colourful clouds. Certain gas giants in reality might theoretically support calmer atmospheric regions at particular altitudes. HD 189733b is not one of them. The temperatures alone make that fantasy collapse immediately, and the radiation environment near the star likely adds another lethal factor. Human bodies are surprisingly vulnerable to ionizing radiation. Earth's magnetic field and atmosphere protect life continuously from solar and cosmic radiation. Without those protections, biological damage accumulates rapidly. HD 189733b receives enormous stellar irradiation because of its extremely close orbit. The planet's atmosphere absorbs much of it, of course, but the overall environment remains extraordinarily energetic. Electronics would degrade, biological tissue would suffer. And all of this happens before considering the chemistry of the atmosphere itself, which contains no breathable oxygen whatsoever. Hydrogen and helium dominate. Even if temperatures somehow became comfortable magically, a human stepping outside without protection would immediately suffocate. Space itself, of course, has no smell because vacuum does not carry airborne molecules, but planetary atmospheres absolutely can contain distinct chemical odours, assuming humans could somehow safely detect them. Scientists studying hot Jupiters, including HD 189733b and similar worlds, believe sulfur compounds may exist within portions of these atmospheres. Hydrogen sulfide in particular becomes interesting because humans know it very well. Hydrogen sulfide smells like rotten eggs. On Earth, hydrogen sulfide appears naturally in volcanic gases, swamps, sewage systems, and certain industrial processes. Even tiny concentrations smell terrible because human noses evolved to recognize sulfur-related decay strongly. Now imagine sulfur compounds mixed into an atmosphere already resembling a supersonic furnace. A blue planet where the rain cuts like glass and the air smells like volcanic sewage. Although honestly, the melting would probably become the larger issue first. There is also the question of gravity. HD 189733b is more massive than Jupiter, which already possesses gravity roughly 2.5 times stronger than Earth's at cloud top levels. Depending on atmospheric altitude and local conditions, gravitational forces on HD 189733b would place enormous strain on human bodies and spacecraft operations. Everything becomes heavier. Movement becomes harder. Atmospheric dynamics intensify further under those gravitational conditions. The entire environment works against survival simultaneously, and yet humans remain fascinated by imagining visits to such worlds. Perhaps because dangerous places reveal reality more clearly somehow. Extreme environments strip away comforting assumptions. They remind us that Earth is not normal simply because it feels normal to us. Earth is gentle. Rarely do we appreciate how gentle. Breathable air, moderate temperatures, liquid water, manageable weather, a magnetic field protecting life, stable sunlight. Relatively calm geology. The deeper astronomers study exoplanets, the more astonishing Earth's habitability begins to appear. HD 189733b helps highlight that contrast dramatically. A world where even the atmosphere itself becomes deadly. Still, despite all these impossibilities, studying such planets remains enormously important scientifically. Because extreme worlds teach us about planetary physics in ways calmer worlds cannot. They test atmospheric models, chemical theories, and ideas about planetary formation. In a strange way, HD 189733b serves as a reminder that planets are not automatically places meant for life. Some worlds exist simply as giant thermodynamic systems shaped by gravity and radiation, and the universe appears perfectly comfortable creating them in enormous variety. One especially humbling realization about HD 189733b is that humanity already knows more about this impossible world than ancient humans knew about many regions of Earth itself. For most of history, oceans remained mysterious. Entire continents stayed unexplored for civilizations living elsewhere. People once feared sailing too far from shore. Now we analyze atmospheric chemistry on worlds orbiting distant stars. That progression is extraordinary. No human being will likely ever stand inside the storms of HD 189733b, and honestly, that is probably for the best. Some places in the universe may exist primarily to be observed rather than visited. Still, the more scientists studied this bizarre blue world, the more another fascinating question emerged. How exactly did astronomers manage to learn so much about a planet they cannot even properly photograph directly? If you pointed even the most powerful ordinary telescope toward HD 189733b and hoped to see a crisp image of the planet floating beside its star, you would probably feel disappointed very quickly. Not because the planet is not there, not because telescopes are weak, but because stars are outrageously bright. The problem astronomers face when studying exoplanets is not usually distance alone. It is contrast. Imagine standing very far away from a lighthouse at night and trying to spot a tiny insect flying beside the beam. That is roughly what exoplanet astronomy feels like. The star dominates everything. Its light floods detectors, overwhelms cameras, and hides nearby planets almost completely. Even giant planets larger than Jupiter become nearly invisible when sitting beside stars millions or billions of times brighter. And yet somehow, despite this absurd challenge, astronomers learn the size, orbit, atmosphere, colour, wind speeds, and weather patterns of HD 189733b. Humanity essentially figured out how to study an invisible world. That is one of the reasons exoplanet science feels almost magical sometimes. The discoveries sound impossible until you understand the methods behind them. And once you do understand them, the science somehow becomes even more impressive. The story begins with starlight. Nearly everything astronomers know about distant planets comes indirectly from studying the light of stars very carefully. Not just brightness, but tiny changes within that brightness. Minute flickers, subtle shifts, patterns hidden inside the light itself. HD 189733b was discovered using one of the most successful techniques in exoplanet science, the transit method. The principle sounds simple. If a planet passes directly between its star and Earth, it blocks a tiny fraction of the star's light for a short time. The star dims slightly, then brightens again once the planet moves away. That is the entire basic idea. But the actual measurements involved are astonishingly delicate. Imagine observing a car headlight from hundreds of kilometers away and trying to detect a fruit fly passing across it. The brightness change is incredibly small. Yet sensitive instruments can detect it, and because the dimming repeats regularly, astronomers can confirm that a planet is orbiting the star rather than random noise or instrument error. HD 189733b turned out to be especially useful because its orbit aligns perfectly from Earth's perspective. Every little over 2 days, the planet passes in front of its star, producing a measurable transit. That regularity became enormously important. Each transit gives scientists another opportunity to gather data, another chance to study the atmosphere, another tiny glimpse into a world no human will ever visit directly. Once astronomers detected the repeating dimming pattern, they could begin calculating the planet's size. A larger planet blocks more light, a smaller planet blocks less. By measuring precisely how much brightness disappears during transit, scientists estimate the planet's diameter. That alone already feels impressive. But then things become far more sophisticated. You see, the planet itself is not the only thing passing in front of the star. Its atmosphere passes too, and atmospheres interact with light. Different gases absorb different wavelengths of starlight. Sodium leaves one signature. Water vapor leaves another. Hydrogen, methane, carbon monoxide, silicates all affect light differently. So when starlight filters through the atmosphere during transit, the atmosphere leaves chemical fingerprints embedded inside the light. Astronomers then analyze that light using spectroscopy. Spectroscopy is one of the greatest inventions in scientific history because it allows humans to determine what distant objects are made of without physically touching them. The technique works because atoms and molecules absorb and emit light at very specific wavelengths. Each chemical element creates its own unique pattern, like cosmic barcodes, or fingerprints, or tiny chemical signatures written directly into starlight itself. By splitting starlight into spectra and examining those patterns carefully, astronomers reconstruct atmospheric composition across impossible distances. This is how scientists detected water vapor in the atmosphere of HD 189733b, how they inferred silicate particles, how they studied atmospheric chemistry, all from light. It is extraordinary when you stop and think about it. Human beings evolved under open skies, worrying mainly about food, weather, and predators. Then eventually someone discovered that light contains hidden information about matter itself, and now we use that knowledge to analyze alien atmospheres across the galaxy. Civilization took a wonderfully ambitious turn somewhere along the line. One especially important tool in studying HD 189733b was the Hubble Space Telescope. Hubble transformed astronomy not only because it sits above Earth's atmosphere, but because it observes the universe with extraordinary precision free from atmospheric distortion. Earth's atmosphere, useful as it is for breathing and not dying, unfortunately blurs astronomical observations constantly. Air turbulence distorts incoming light, making precise measurements difficult. Hubble avoids that problem by orbiting above the atmosphere entirely. And when Hubble observed HD 189733b, scientists began uncovering astonishing details. They detected atmospheric components. They measured visible light scattering. They estimated the planet's blue coloration. Eventually, they even began studying weather behavior itself. This is where astronomy starts sounding increasingly unreasonable in the best possible way. Researchers analysed infrared emissions from the planet during different orbital phases. Infrared light corresponds strongly to heat, so by measuring infrared brightness carefully over time, astronomers could estimate temperature distributions across the atmosphere. Essentially, they created rough thermal maps of a planet 64 light-years away. A planet they cannot directly photograph properly, and those maps revealed something surprising. The hottest region of the atmosphere was not exactly where expected. Instead of sitting directly beneath the star, the hottest area appeared shifted eastward. That implied the atmosphere was transporting heat rapidly around the globe through powerful winds, and from there, scientists began estimating atmospheric circulation speeds, again through light. At one point, researchers used the Doppler effect to study atmospheric motion itself. The Doppler effect is the same physical principle responsible for changing pitch when an ambulance drives past you. As the sound source moves closer, waves compress. As it moves away, waves stretch. Light behaves similarly. If atmospheric gases move toward Earth, their spectral lines shift slightly toward blue wavelengths. If they move away, the lines shift toward red. By measuring tiny spectral shifts during transit observations, astronomers estimated wind speeds within the atmosphere. Those measurements suggested winds moving thousands of miles per hour. Supersonic weather, measured from another star system. There are moments in science where human intelligence genuinely becomes difficult not to admire. Of course, none of this work happens easily. Exoplanet observations require enormous precision. Tiny fluctuations in instruments, stellar activity, background noise, and statistical uncertainty all complicate the data. Stars themselves are active objects. They pulse slightly, flare occasionally, and produce their own spectral signatures. Scientists must carefully separate planetary signals from stellar behavior. Imagine trying to study a firefly while someone repeatedly shines a flashlight into your eyes and occasionally shakes the entire room. That is closer to the challenge astronomers face, and yet they keep succeeding. Another important observatory involved in studying HD 189733b was the Spitzer Space Telescope, which specialized heavily in infrared observations before its retirement. Spitzer allowed astronomers to examine thermal emissions from exoplanets with unprecedented sensitivity. By observing the planet during different stages of orbit, scientists learned more about heat distribution and atmospheric circulation. The deeper researchers looked, the more complicated and dynamic the atmosphere appeared. One fascinating technique used in exoplanet science involves observing what happens when the planet passes behind the star, an event called secondary eclipse. During normal observation, astronomers receive combined light from both the star and planet, but when the planet slips behind the star temporarily, its contribution disappears. By comparing brightness before, during, and after the eclipse, scientists isolate the planet's own emitted or reflected light. That is how researchers estimated HD 189733b's blue color. Think about how astonishingly delicate this process is. The difference in brightness caused by the planet alone is tiny compared to the overwhelming glare of the star. And yet scientists measured it. The resulting data suggested the deep cobalt blue appearance that made the planet famous. Astronomy often feels like an exercise in extracting impossible amounts of information from almost nothing. Tiny dimming patterns become planetary sizes. Faint spectral lines become atmospheric chemistry. Minuscule infrared variations become climate maps. Starlight itself becomes a storytelling tool, and the stories hidden inside that light turned out to be far stranger than anyone expected. One especially humbling aspect of exoplanet science is how recent it all is. The first confirmed planet orbiting a sun-like star was discovered only in 1995. That is astonishingly recent. Humanity built cathedrals, crossed oceans, invented physics, split the atom, and walked on the moon before finally proving that planets orbit other stars. Now, only a few decades later, we analyse alien atmospheres and discuss weather systems on worlds dozens of light years away. Scientific progress can accelerate breathtakingly fast once key technologies emerge, and it continues accelerating now. New observatories like the James Webb Space Telescope are dramatically expanding humanity's ability to study exoplanet atmospheres. Webb's infrared sensitivity allows researchers to examine chemical compositions with far greater precision than previous instruments. The future of exoplanet science may include detailed studies of smaller rocky worlds, potentially even Earth-sized planets with atmospheres resembling our own. Scientists hope to search eventually for biosignatures, atmospheric combinations difficult to explain without biological activity. Oxygen alongside methane, for example. Chemical disequilibrium potentially hinting at life, and techniques refined on extreme planets like HD 1899733b help build that future. In many ways, hot Jupiters became training grounds for exoplanet astronomy, because they are easier to detect than smaller planets. Their large sizes produce stronger signals. Their close orbits create frequent transits. They are loud planets, astronomically speaking, easy to notice first. And through studying them, astronomers learned how to decode planetary atmospheres generally. Even terrifying worlds can become valuable teachers. One of the most beautiful things about astronomy is that it transforms light into understanding. A photon leaves a distant star system. It crosses space for decades. Eventually it reaches a telescope orbiting Earth. Scientists analyze tiny variations hidden within it, and suddenly humanity knows there is a blue world where supersonic winds carry molten glass sideways through the atmosphere. All because of a few faint changes in ancient starlight. That still feels miraculous no matter how carefully you explain the physics. When astronomers first began discovering planets around other stars in the 1990s, they expected the universe to behave sensibly. That turned out to be a mistake. It was a reasonable mistake, admittedly. At the time, humanity possessed exactly one known example of a planetary system, our own. So scientists naturally assumed other solar systems would probably resemble it, at least roughly. Small rocky planets near stars, large gas giants farther away, neat stable orbits, reasonably predictable arrangements. Instead, the universe immediately responded with something far stranger. The first exoplanets astronomers found in large numbers were not calm Earth-like worlds or distant Jupiters slowly circling their stars over decades. They were giant planets orbiting absurdly close to their stars. Massive gas giants completing full orbits in just days. Worlds so hot their atmospheres glowed. Planets blasted by stellar radiation so intensely that entire weather systems became monstrous. Astronomers eventually named them hot Jupiters, and they completely shattered existing theories about how planetary systems were supposed to form. HD 1899733b belongs to this strange family. In fact, it became one of the most famous hot Jupiters ever discovered precisely because it combined several qualities at once. Large enough to study easily, close enough for detailed observations, and bizarre enough to capture public imagination immediately. But as scientists continued surveying the galaxy, they discovered that HD 189733b was only one member of an entire population of impossible worlds, and some of its relatives are even stranger. To understand why hot Jupiters shocked astronomers so deeply, it helps to think about how our own solar system formed. The early Sun was surrounded by a rotating disk of gas and dust called the protoplanetary disk. Over time, particles collided, merged, and gradually built larger bodies. Closer to the Sun, temperatures remained too high for volatile compounds like water ice to condense easily. Rocky planets formed there instead. Farther outward, beyond what astronomers call the frost line, temperatures became low enough for icy materials to accumulate rapidly. Giant planets formed in those colder regions where abundant material allowed massive cores to gather thick atmospheres of hydrogen and helium. That is why Jupiter and Saturn orbit far from the Sun. The theory worked beautifully. Then astronomers found giant planets practically touching their stars, and everyone collectively had to rethink things. Hot Jupiters should not exist where they are found, at least not according to earlier assumptions. A gas giant orbiting extremely close to its star experiences intense radiation, violent tidal forces, and difficult formation conditions. The inner regions of planetary systems simply do not contain enough cool material traditionally required to build such enormous planets directly. So how did they get there? Scientists now believe many hot Jupiters probably formed farther away, before migrating inward over time through gravitational interactions with the protoplanetary disk or neighbouring planets. In other words, entire planets move dramatically after formation. Planetary systems are not static, peaceful clockwork arrangements. They are chaotic, restless, dynamic. Worlds migrate, orbits destabilize, gravity rearranges entire systems over millions of years. Our own solar system now appears comparatively calm by galactic standards, which is mildly reassuring, though space still seems perfectly capable of producing terrifying surprises whenever it feels like it. Hot Jupiters themselves are fascinating, partly because they push atmospheric physics into extreme territory. Their close proximity to stars creates conditions unlike anything found in our solar system. HD 209458b, for example, became famous because astronomers discovered its atmosphere was actively escaping into space. The star was essentially stripping the planet away gradually through intense radiation. Imagine a world evaporating beneath its own sun. Another famous hot Jupiter, WASP-12b, orbits so close to its star that tidal forces may be physically deforming it into an egg-like shape. Not metaphorically, actually stretching the planet itself. The atmosphere of WASP-12b grows so hot that molecules break apart under the star's radiation. Some models suggest carbon-rich chemistry that could produce exotic forms of material entirely unlike Earth environments. Then there is KELT-9b, which almost stops feeling like a planet altogether. KELT-9b is one of the hottest exoplanets ever discovered. Its dayside temperatures exceed many stars. Let that sink in for a moment. A planet hotter than some stars. Temperatures there climb beyond 4,000 degrees Celsius, hot enough to vaporize metals into the atmosphere. Researchers detected iron and titanium atoms floating within its superheated skies, not compounds, atoms. The atmosphere itself becomes so energetic that ordinary molecular chemistry starts collapsing. KELT-9b essentially exists on the edge between planet and stellar furnace, and somehow, despite all that insanity, it still technically counts as a planet. The universe really does enjoy exploiting loopholes in human classification systems. Another remarkable world is 55 Cancri E, a rocky planet so close to its star that parts of its surface may consist of molten lava oceans. Temperatures there become high enough to melt rock directly across enormous regions. Imagine entire seas of liquid magma glowing beneath black skies. Again, reality casually outperforming science fiction. Some exoplanets likely experience iron rain. Others may contain atmospheric clouds made of vaporized minerals. There are planets with years lasting only hours, worlds orbiting dead stars, planets circling binary suns, even rogue planets drifting through interstellar darkness entirely alone, without any star at all. Once astronomers started looking seriously, the galaxy immediately became much stranger than expected, and hot Jupiters played a major role in that realization, because they were among the easiest planets to detect initially. Large planets create stronger gravitational wobbles in their stars, close orbits produce frequent transits, their atmospheres become easier to analyze because stellar radiation inflates and energizes them dramatically. Hot Jupiters are loud planets, observationally speaking. They announce themselves, which means humanity's first glimpse into alien solar systems came through some of the weirdest worlds possible. It is a bit like trying to understand Earth by first discovering only volcanoes and hurricanes. Still, those discoveries transformed astronomy permanently. Before exoplanets, planetary science remained largely confined to our solar system. Scientists studied variations among familiar worlds, but still unconsciously treated our system as typical. Now we know typical may not really exist. The galaxy appears astonishingly diverse, and perhaps that diversity is one of the most emotionally fascinating things about modern astronomy. For thousands of years, humans looked at stars and wondered whether other worlds existed. Now we know the answer is yes, and not merely a few worlds. Billions upon billions of them. Many utterly unlike anything imagined historically. Hot Jupiters also forced scientists to reconsider planetary habitability indirectly. Early science fiction often imagined life thriving primarily on Earth-like planets around Sun-like stars. But once exoplanet diversity exploded, researchers realized habitable conditions might arise under far more varied circumstances than previously assumed. Moons orbiting giant planets, tidally locked worlds around red dwarfs, ocean planets, subsurface environments. Exoplanet science dramatically expanded the imagination of where interesting conditions might emerge. Not on hot Jupiters themselves, certainly. Most appear catastrophically hostile, but studying extremes teaches scientists how planetary systems behave generally, and every strange world adds another piece to the puzzle. One especially interesting question involves whether hot Jupiters disrupt the formation of smaller rocky planets nearby. Since giant planets likely migrated inward dramatically, they may have scattered or destroyed material in the inner system during that journey. Imagine a Jupiter-sized world ploughing through developing planetary orbits like a gravitational bulldozer. Entire planets may have been ejected from systems or consumed by stars during such migrations. Planetary systems can be surprisingly violent places. HD 189733b itself may have altered the architecture of its system profoundly during its migration inward long ago. What other worlds once existed there? Did smaller planets form before being destabilized? Were moons stripped away? Did the planet once orbit peacefully farther from its star before gravity dragged it inward toward atmospheric madness? Astronomy often reveals only the surviving outcome, not the full history. And that history may involve extraordinary chaos. There is also something strangely humbling about realizing how quickly human expectations failed once observations improved. For centuries, people assumed the universe probably resembled our local environment broadly. Then telescopes improved slightly, and suddenly, astronomers found planets where it rains molten glass sideways beneath blue skies. Reality appears under no obligation to remain intuitive, and perhaps that is part of why astronomy feels so endlessly fascinating. Every improvement in technology reveals environments more bizarre than expected. The James Webb Space Telescope is already beginning to analyze exoplanet atmospheres in unprecedented detail. Future telescopes may detect weather systems, atmospheric circulation patterns, and chemical signatures on smaller rocky planets. One day, humanity may identify unmistakable evidence of life elsewhere, Or perhaps we will simply keep discovering increasingly terrifying weather. Honestly, either outcome feels plausible at this point. One fascinating detail about hot Jupiters is that despite their violence, they may not survive forever. Many orbit so close to their stars that tidal interactions gradually alter their orbits over time. Some may eventually spiral inward completely, consumed by the very stars they circle. Imagine a planet spending millions of years enduring impossible storms before finally falling into its star and vanishing forever. Cosmic existence can feel surprisingly dramatic when viewed on long enough timescales. Yet throughout all these discoveries, HD 189733b remains special. Not necessarily because it is the hottest, or the largest, or the most extreme overall, but because it combines scientific importance with vivid imagination better than almost any other exoplanet. A blue world, glass rain, supersonic winds, permanent day and endless night. It feels emotionally real in a way many exoplanets do not. For most of human history, the universe felt strangely orderly. The stars moved predictably across the sky. The planets wandered in recognizable paths. Ancient astronomers mapped the heavens carefully because the cosmos appeared structured, almost disciplined. Even when humans did not fully understand what they were seeing, the sky still carried a sense of stability. And in many ways, that perception shaped how people imagined reality itself. Earth sat at the centre once, according to early models. Then the Sun replaced Earth at the centre of the solar system. Eventually, astronomers realized the Sun itself was only one ordinary star among hundreds of billions inside the Milky Way. Each discovery pushed humanity outwards psychologically. We became less central each time. But something interesting happened during those earlier revolutions. Even as humans lost their physical central position, we still quietly assumed our solar system was probably fairly normal, reasonable, representative. The planets around us became the template for what planets were supposed to be. Rocky worlds near stars, gas giants farther away, stable orbits, moderate planetary behaviour. Even science fiction often followed those assumptions unconsciously. Alien worlds tended to resemble Earth in one way or another, because Earth remained the only detailed example anyone truly knew. Then exoplanets arrived, and the universe immediately stopped behaving politely. Hot Jupiters like HD 189733b changed astronomy profoundly because they shattered the comforting assumption that planetary systems naturally organize themselves like ours. Instead, the galaxy revealed itself as a place filled with extremes, worlds migrating inward toward their stars, planets hotter than some stars themselves, atmospheres made of vaporized rock, supersonic weather systems, tidal locking, iron rain, molten surfaces, entire categories of planets that no one predicted confidently beforehand. The moment astronomers started discovering real exoplanets in large numbers, planetary science transformed from a study of familiar neighbouring worlds into something much larger, something stranger, something almost overwhelming in scale and diversity. HD 189733b became one of the symbolic worlds of that transformation because it captured the public imagination so perfectly. A blue planet where it rains glass sideways sounds fictional in exactly the right way. It feels emotionally impossible while remaining scientifically real, and that combination matters enormously because science advances not only through data but through imagination. Certain discoveries reshape how humans emotionally picture reality itself. The first images of Earth from space changed people psychologically. Suddenly humanity saw the planet as one fragile sphere floating in darkness. The discovery of exoplanets created a similar shift, though slower and quieter. It revealed that worlds are everywhere, not just stars, worlds, Actual places with skies, weather, chemistry, gravity, storms, and histories. Before exoplanets, planets felt local. Now they feel cosmic. And once humanity understood that, the night sky changed permanently. Every star suddenly became a possible system of worlds, every point of light potentially surrounded by planets completely unlike our own. That realization still feels astonishing even now, especially because exoplanets turned out to be so wildly creative. The universe did not merely repeat Earth over and over again, it experimented, aggressively. One of the biggest scientific impacts of hot Jupiters involved planetary formation theory. Before their discovery, astronomers believed they understood how planetary systems formed reasonably well. Then hot Jupiters appeared in places they absolutely should not exist according to earlier models. That forced scientists to rethink everything from orbital migration to gravitational interactions inside protoplanetary disks. Entire theories evolved because one category of strange planets refused to behave correctly. Science works best when reality disagrees with expectations. That disagreement forces improvement. And HD 189733b became part of that process. The planet helped scientists refine atmospheric models under extreme conditions. Researchers learned how heat redistribution works on tidally locked worlds. They developed techniques for studying exoplanet atmospheres through spectroscopy and thermal mapping. Every strange exoplanet expanded the toolkit. And perhaps most importantly, these discoveries made scientists realize how little humanity had previously understood about planetary diversity. Earth is not the default setting for planets. That may be one of the most important lessons modern astronomy has taught us. Earth feels normal because we evolved here. But the galaxy contains worlds operating under physical conditions so different from ours that even basic concepts like rain, weather, and day-night cycles become unrecognizable. And once you internalize that, something subtle changes in how you think about existence. The universe stops feeling designed around human expectations. Instead, humanity becomes one small local outcome among endless possibilities. Oddly enough, many people find that comforting rather than frightening. There is something emotionally freeing about realizing the cosmos is larger and stranger than our assumptions. HD 189733b also helped change public engagement with astronomy, because it gave people a vivid mental image. For decades, astronomy sometimes struggled with abstraction in public imagination. Galaxies, quasars, and black holes fascinated people intellectually, but exoplanets felt personal. They are worlds, places. Even when completely uninhabitable, they still trigger the imagination differently than stars do. A star is enormous and distant. A planet feels visitable emotionally, even if physically impossible. So when people heard about a blue world with glass rain and supersonic winds, astronomy suddenly felt less abstract. The galaxy became populated with actual environments, actual weather, actual skies. And every new exoplanet discovery expanded that sense further. Some people began wondering whether life exists elsewhere. Others became fascinated by atmospheric chemistry or planetary physics. And many simply enjoyed the strange creativity of reality itself, because honestly, the universe seems far more imaginative than most fiction writers dared to predict historically. Another profound shift caused by exoplanets involves probability. Before exoplanet discoveries, discussions about alien life remained highly speculative because nobody even knew how common planets were. Now we know planets are everywhere. Current estimates suggest there may be hundreds of billions of planets in the Milky Way alone, possibly trillions across the observable universe, and among those unimaginable numbers, at least some likely possess conditions suitable for liquid water, potentially life, perhaps intelligence. That realization changed the emotional scale of the cosmos permanently. Humanity may still be alone, but statistically the universe suddenly started looking much more crowded than before. Even hostile worlds like HD 189733b contribute to that realization, because they demonstrate how varied planetary environments can become. Once scientists saw how many impossible worlds existed, they also realized habitable worlds might emerge under broader conditions than previously imagined. The universe became less predictable, and therefore more open to possibility. There is also something philosophically interesting about the fact that humans discovered such bizarre worlds so quickly after gaining the ability to look properly. The moment our instruments improved enough, the galaxy immediately revealed atmospheric nightmares, lava oceans, rogue planets, and giant worlds orbiting stars every few days. It is almost as though reality had been waiting patiently behind a curtain saying, "You have absolutely no idea what's out here," and perhaps we still do not. Modern astronomy likely represents only the beginning of understanding planetary diversity. Future telescopes may discover environments even stranger than anything known today, worlds with atmospheric chemistry currently unimaginable, planets orbiting exotic stellar remnants, subsurface ocean systems beneath frozen crusts, artificial atmospheric signatures perhaps. We genuinely do not know what the universe ultimately contains. That uncertainty itself became one of the greatest gifts of exoplanet science. The cosmos stopped feeling complete. For a while during the 20th century, many scientists worried astronomy might eventually become mostly finished. The basic structure of stars, galaxies, and gravity seemed increasingly understood. Then exoplanets exploded into view and reminded humanity that reality still contained vast undiscovered territories. Entire categories of worlds waited unseen around distant stars. And suddenly astronomy felt open-ended again, limitless. HD 189733b helped symbolize that new era because it represented a planet no one would have predicted emotionally beforehand, a blue atmospheric giant where the weather itself becomes catastrophic, beautiful and hostile simultaneously, familiar enough to imagine, alien enough to feel impossible. One especially humbling aspect of all this is how tiny the observational signals actually are. Everything humanity knows about HD 189733b emerge from faint flickers of starlight, tiny spectral changes, minuscule brightness dips, ancient photons crossing space for decades before reaching telescopes near Earth. From those nearly invisible clues, humans reconstructed an entire world. That achievement says something extraordinary about science itself. Human beings are small, physically fragile, short-lived, confused surprisingly often, and yet somehow capable of understanding realities far beyond direct experience. We learned how to decode alien atmospheres without leaving our planet. That remains astonishing no matter how familiar the discoveries become. There is another emotional layer to exoplanet discoveries too. For centuries, stars represented distance and mystery in human culture. People looked upward and wondered what existed out there. But the answers remained inaccessible. Now the mystery has changed shape. We no longer ask whether worlds exist around stars. We ask what those worlds are like. That is a profound transition. The night sky transformed from emptiness into geography. Unknown geography certainly, but geography nonetheless. And somewhere within that cosmic geography lies HD 189733b, endless storms, blue skies filled with silicate haze, supersonic winds carrying molten glass through the atmosphere. A planet so strange it helped humanity realize the universe itself was stranger than expected. In some ways, that may be the real importance of worlds like this. Not merely their scientific details, but their ability to expand imagination itself. They remind us that reality remains far larger than the tiny, comfortable slice humans experience daily. The cosmos is not obligated to resemble Earth. It creates worlds endlessly, some gentle, some violent, some probably beyond current imagination entirely. And among those countless worlds, humanity exists on one unusually calm little planet beneath ordinary rain, and manageable skies, which suddenly feels much more precious once you understand what else the universe allows. And perhaps that is the strangest effect exoplanets had on human thinking. The farther we looked outward, the more extraordinary Earth itself began to appear. Somewhere tonight, far beyond the reach of human cities, beyond the moon, beyond the planets of our own solar system, beyond the distant edge of the Oort cloud where even sunlight grows thin and weak, a storm is still raging. It has been raging long before any human being existed. And unless something extraordinary changes, it will likely continue long after humanity itself is gone. Around a distant orange star, HD 189733b circles endlessly through darkness. One side of the planet remains locked beneath eternal daylight while the other lives in permanent night. Between them, the atmosphere never rests. The winds continue screaming across the globe faster than sound. Silicate particles still condense high in the atmosphere, and somewhere inside those blue clouds, glass is still falling sideways through an alien sky. There is something strangely calming about that thought. Not because the planet itself is calm, obviously. It is one of the least calm places humanity has ever discovered. The weather there would tear apart almost anything humans have ever built. Temperatures rise beyond survival instantly. The atmosphere behaves like a planetary furnace wrapped inside a hurricane. And yet, from far away, all of that violence becomes silent. Just another blue world drifting through space. Astronomy does that sometimes. It takes unimaginable chaos and wraps it in distance until it feels peaceful again. You can look at images of galaxies colliding, stars exploding, black holes consuming matter, and somehow the sheer scale of space softens everything into quiet beauty. Perhaps that is one reason people find the night sky comforting. The universe is full of catastrophic things, but they happen so far away that they become gentle to contemplate. Even HD 189733b, with its endless storms and molten glass rain, eventually transforms into something almost meditative when viewed from Earth. A reminder that reality is larger and stranger than our daily worries. Right now, somewhere on Earth, someone is probably lying awake worrying about emails, unfinished work, bills, awkward conversations, tomorrow morning's alarm, or whether they accidentally said something embarrassing 3 years ago that nobody else remembers. Meanwhile, 64 light-years away, an entire planet is enduring supersonic storms beneath permanent blue haze. The scale difference becomes oddly soothing. Human life feels very large when viewed from inside it, but astronomy quietly reminds us that existence itself stretches far beyond the boundaries of our routines and anxieties. There are worlds no human will ever touch, storms no human ear will ever hear, clouds drifting through atmospheres made of substances and temperatures evolution never prepared us to imagine. And somehow, against overwhelming odds, tiny creatures on Earth learned enough physics to discover them. That may be the most astonishing part of this entire story. Not the glass rain, not the supersonic winds, not even the beautiful blue atmosphere, but the fact that humanity figured it out at all. Think about how improbable that really is. A species that evolved on one small rocky world eventually built telescopes capable of analysing starlight across trillions of kilometres. Humans learned how to split light into spectra, measure invisible wavelengths, detect tiny brightness fluctuations, and reconstruct entire alien atmospheres from faint photons crossing space for decades. We discovered weather on another world without ever leaving our own. Civilization can feel messy and chaotic sometimes. News cycles become exhausting. Technology overwhelms people. The internet occasionally makes humanity appear deeply unprepared for collective responsibility. And then astronomy quietly reminds you that the same species arguing online about nonsense also built instruments capable of studying a planet where it rains molten glass. Humans are complicated, but wonderfully curious. That curiosity carried us from ancient campfires beneath unknown stars all the way to exoplanet science. Thousands of years ago, people looked upward and wondered whether worlds existed around other stars. Now we know. And the answer turned out to be far stranger than expected. The galaxy contains lava worlds, frozen giants, rogue planets drifting through darkness alone, and hot Jupiters wrapped in endless storms. There are likely billions upon billions of planets scattered across the Milky Way, each with its own history, chemistry, weather, and orbit. Some may be quiet, some violent, some perhaps capable of supporting life. Others, like HD 189733b, seem determined to demonstrate how hostile the universe can become while still looking oddly beautiful from a distance. And maybe that beauty matters too, not because dangerous things are secretly good, but because the universe does not separate beauty and violence the way humans often do. Volcanoes glow beautifully. Lightning illuminates storms magnificently. Even Earth itself appears peaceful from orbit despite everything happening below. HD 189733b belongs to that same category of cosmic contradiction, a world terrifying up close, beautiful from afar, blue enough to resemble calmness while hiding one of the most violent atmospheres humanity has ever studied. There is also something humbling about realizing how many worlds remain undiscovered. HD 189733b became famous because current technology allowed astronomers to notice it relatively easily. Large planet, close orbit, strong atmospheric signals. But there are undoubtedly stranger places waiting farther out. Future telescopes will uncover more impossible worlds, new atmospheres, new chemistry, new forms of weather beyond anything currently imagined. The universe has not finished surprising us yet. In fact, exoplanet science is still very young. The first confirmed planet orbiting a sun-like star was discovered only a few decades ago. That means humanity went from wondering whether exoplanets existed at all to analysing alien weather systems in roughly one human generation. Imagine what astronomy may know a century from now, or 1,000 years. Perhaps future scientists will map cloud systems on Earth-like planets routinely. Perhaps they will identify unmistakable biosignatures somewhere distant. Perhaps entirely new categories of worlds still hidden from current instruments will emerge. The night sky may become increasingly populated not with stars alone, but with known places, actual worlds, and somewhere among those countless worlds, HD 189733b will remain one of the early landmarks in humanity's journey outward. The blue planet where it rains glass, the world that helped teach humans how to read alien atmospheres, the storm that never ends. And tonight, while Earth turns quietly beneath ordinary clouds and ordinary rain, that distant atmosphere continues moving exactly as it always has. The star still hangs fixed above one hemisphere. The night side remains dark. The winds keep circling the globe. Silicate particles continue racing through the sky. And from unimaginably far away, a few photons carrying traces of that world are still crossing the darkness toward Earth. Tiny fragments of ancient light, travelling silently for decades, eventually reaching telescopes built by curious creatures beneath another sky. There is something comforting about that connection somehow. The universe can feel impossibly large, yet light still links distant worlds together. And maybe tonight, as you settle deeper into bed and let your thoughts drift more slowly, it is nice to remember that reality is far bigger than the walls around you right now, far bigger than schedules and stress and unfinished tasks. Beyond Earth's atmosphere, beyond our solar system, beyond the familiar stars overhead, entire worlds are still turning quietly through space, some frozen, some burning, some perhaps peaceful, and one of them right now is wrapped in endless blue storms where glass falls sideways forever through the dark. Thank you for spending this journey with me tonight, and wherever you are in the world, I hope the skies above you are considerably gentler than the ones surrounding HD 189733b. Good night.